Okay, Chris, can you hear me? Oh, okay, good. I see you are nodding. All right, so we can start right now, right? Okay, I'll start now. Okay, good morning, good afternoon, and good evening, everyone. Welcome to the 6th ACM IEEE International Conference on Internet of Design and Implementation, IoTDI 2021. I'm a general co-chair of this conference. My name is Ha-Ying Shen. I'm from the University of Virginia in in USA. The other general co-chair is Dr. Valerie Isny. She's from INRIA, France. Unfortunately, she cannot be here now. She asked me to say hello to everyone here. Since 2017, IoTDI has successfully established itself as a leading venue for publishing high-quality work on a wide range of system-related issues related to IoTs. This year, IoTDI is again co-located with CPS-IoT Week. And like last year, the conference is held virtually due to the COVID-19 pandemic. Still, we hope the event will foster the interaction we are used to before. We are very excited to see high quality technical papers, demos, and posters presented and will be presented in the conference. In the virtual conference, I would like to indicate something you want to pay attention. How to participate. Please keep an eye on our website and on the website of CPS IoT Week. The website will give you guidance about how to join the virtual conference. In Slack, it has one channel per paper, plus other channels for discussion and information dissemination. Zoom is where the main action is. In Zoom, we have live presentations of papers, Q&A sessions, and virtual coffee breaks. The IoT event is made possible by the teamwork of many volunteers. We are happy to offer the IoTDI 2021 Outstanding Service Awards to the following members of the organizing committee. Technical program chairs, Dr. Tao Gu and Dr. Chris Stewart. Poster and demo chairs, Dr. Kang Chen and Dr. Amy Murphy. Publicity chairs, Dr. Georgios Balakakis and Dr. Yuan He, Dr. Jingwei Liu. Social media chairs, Dr. Lei, Dr. Zhao Li. Web chair, Dr. Chen Xiqiu. Publication chair, Dr. Jia Rao. Virtual conference working group leaders, Dr. Ning Wang and Dr. Hasna Naman. We would like to acknowledge the significant contribution from the members of the organizing committee. We also would like to thank the steering committee for guiding the organizing activities of this conference, especially Dr. Tariq Abdalza and Dr. Hui Li. Finally, we would like to thank you, the authors and attendees, for your contribution and participation. Without you, the conference would not be possible. Thank you so much. And further, we would like to thank everyone involved in the organization of CPS IoT Week for this support. We look forward to meeting you all in this virtual conference and in our physical conference in the future. Please enjoy the IoTDI 2021 conference. With that, I hand it over to TPC chairs.
All righty. let me double check that I am not muted. Great. So this year I had the honor of serving as a TPC co-chair, and that honor was made all the much better by my partner, Tao Gu. Tao is very longstanding member of this community, and unfortunately is not able to be here today, but has taken on leading a large center. Um, and uh, it, I can't overstate how much I enjoyed working with Tao, and how much his advice really helped me both personally in my own career and helped us craft this program. So uh, in total, we had 74 submissions this year from 10 countries and 4 continents. And we decided to accept 19 full papers for a 25% acceptance rate. This year, we had our program committee, I'm just listing here, did a really great job. We ensured that each paper that we considered deeply had, in the common case, 4 reviews, definitely no less than 3 reviews. And our TPC was just, everybody worked really hard making sure that we got reviews for everything and that we had expert opinions for all of the papers that were submitted. So the way that the reviewing worked was we had the 74 submissions initially, and we did round 1, where each paper received either 2 or 3 reviews. And based on the initial discussion period in round 1, papers that had some amount of support were moved forward to round 2 for a second round of review and consideration. And at that point in time, we had enough feedback that we were able to accept 14 papers immediately. And we reserved another set for discussion at the meeting. Well, all of the other remaining papers were discussed at the TPC meeting. And from that set, we accepted 5 more. So some of the themes that happened with this year's submissions, I'd like to actually take a pause here and say thank you to everyone that is both a presenting author today, and congratulations to those, because the cut was incredibly rigorous, and you all should be very proud of your IoTDI papers and making it past that cut this year, and we're certainly happy to learn from you. And I'd also like to thank all of the authors that submitted papers, including papers that were accepted and rejected, because it is only by going through this fire that we ended up with such a great program. And so we encourage everybody to come back and continue to participate in the community and continue to help grow our efforts in this space. Some trends that we observed across all of the papers ultimately led to the paper sessions that we went with. So security and privacy are still very important topics to this community. We actually have 2 sessions that relate to security for IoT devices, cybersecurity in particular. And this privacy is an emerging issue as well, as people are beginning to look at data being collected in the wild and whom that data is being produced by, and what guarantees we can provide for those. That's session 3 today. Edge computing is obviously a related topic, and we'll have 2 sessions on edge computing. I think this has been a long-standing tradition in our community. AI/ML for IoT, much like the keynote that we just saw earlier from Matt Welsh, this is an emerging area. This year, we were really excited to get a lot of really cool papers on topics that are not just about performance and power, but also about the interaction with humans. So human in the loop, where we're talking about issues like fairness. And then finally, of course, IoTDI is going to be concerned with networking as well. So some notes for presenters. please arrive to your Zoom session 10 minutes early. You have the ability to present live or to present your pre-recorded video. If you are going to present live, or in either case, we ask that you please send a Zoom message, a private Zoom message to your session chair. By the way, I am session chair for the first session, with your name and a bio for the introduction so that we can have seamless introductions. A reminder, which I've already communicated with all of you, 20 minutes for the talk, 5 minutes for questions after. We really want to try to stay on time, and we'll give verbal warnings with about 2 minutes left. So last but not least for today, I'd like to present our best paper awards. And so the process for this was that we took a selection committee that was a subset of the TPC. And after deciding which papers were accepted, we applied another filter based on the reviews, where we looked for papers that had 4 or 5 reviews, and we looked at the papers that had that were the highest ranking papers among those that received many reviews. And by the way, these some of these reviews may have also been informal reviews that were not actually reflected in the feedback. So those papers that had the 5 highest rankings were discussed. We actually sat down as a committee and we met and we discussed all of these papers in terms of their merits, their impact, and their novelty. Especially novelty proved to be an important concern that the committee was really interested in. And so our winners are in session 7, when video meets inertial sensors, zero-shot domain adaptation for finger motion analytics with inertial sensors. And in session 6, MilliEye, a lightweight millimeter wave radar and camera fusion system for robust object detection. So we'll be in touch with the authors to get your contact information so that we can send out your physical awards after the conference. So again, I won't bore us too much with how to engage with Q&A. We've all been on Zoom for more than long enough now, so we know not to do things like to use the public Zoom chat for our questions, but instead to interact through Slack or through a private chat with the session chair. I will direct you to the IoTDI website where we have links to the papers available. So with that said, let's all try to enjoy the conference. And congratulations to our best paper winners. And we'll get started with session 1. So moving right into the session, we'll start maybe 3 minutes early, maybe a little bit too early. So I'll wait just for 1 minute in case others are hoping to join for the session. And so Panos is the presenter for the next session. Can you share your screen, Panos?
Actually, I have submitted a pre-recorded video.
Okay, you'd like to do the pre-recorded. So then, Ning, can you set that up? Just double check that. Okay. So Ning is setting that up. Excellent. So Panos Chatzgiannis is a PhD student at George Mason University and is currently on internship with Facebook, working with the DM payment system. His research is focused on cryptography and blockchains, including anonymity on blockchains and efficient crypto operations on resource-constrained devices. And today he will talk to us about black box IoT through the pre-recorded video. Go ahead and start it.
Hello, I am Panos from George Mason University, and I will be talking about our paper, Black Box IoT, Authentication and Distributed Storage of IoT Data from Constrained Sensors, joint work with Fotini Baltimci, Konstantinos Kollias, and Angelos Stavro. So the setting our work is considering is the industrial IoT setting, for example, manufacturing, agriculture, oil and gas, etc., where sensors, which are devices such as temperature sensors, infrared sensors, etc., are broadcasting their measurements to gateway devices, which in turn submit their data to a local or cloud database. So all the sensors in the setting are typically pretty constrained, can be battery operated or with very limited storage and processing power, and have unreliable clocks. We particularly focus on the most constrained class of such devices, which are referenced as class 0 devices, according to RFC 7228. And these devices have less than 10 kilobytes of RAM. Then, as we saw before, these constrained devices broadcast their collected data to gateways, which we will refer to as aggregators. And these devices are typically more powerful compared to sensors, and their job is to process or aggregate collected data and then submit them to a database. However, in this scenario, this database can be vulnerable to attacks and can be an easy target for denial of service, security breaches, etc. So as a solution, the IoT data can be stored in a distributed fashion. And to achieve this property, instead of a database, we can consider a blockchain, which is a distributed immutable ledger, is tamper-proof, decentralized, and can be utilized to detect any inconsistencies. But while this might offer security in the higher level of the system, there might still be security vulnerabilities in the lower levels. In particular, an attacker might attempt to tamper with a data collection process. So we would like to ensure that the originating data comes from a legitimate source. And this requires us to authenticate the sensor data packets to maintain integrity, non-repudiation, and data provenance. However, the challenge now for authenticating the sensor data is that these devices can have very limited resources in the industrial IoT. So the typical asymmetric authentication schemes used for digital signatures can be too expensive for the sensors. So given the setting and the challenges we saw earlier, we propose a black box IoT, which is a complete blockchain-based system for authenticating IoT data. To achieve this, we use a slightly modified version of the Hyperledger Fabric blockchain framework. And our work includes a comprehensive threat model to show its security. And most importantly, as our goal is to authenticate extremely constrained devices, we demonstrate practical results on real-world devices. And the key component of our system is a novel signature scheme based on hashing, which is a much cheaper operation compared to classic asymmetric key operations. So before we go into our actual hash-based signature scheme, we will first see the concept of a hash chain, which originates back from Lamport passwords in 1981. So let's consider the client who wants to generate a series of one-time passwords, meaning that these passwords can only be used once to log into a server, because reusing them would be insecure. So the client creates a seed key, kn, then hashes it, creating a hash of kn, and then hashes it again to create a double hash, and so on and so forth. So this essentially creates a hash chain of hashes. And if the client does this hash n times, it will create a chain of a length n plus 1, where the last key will be hashed n times from the seed. And for simplicity notation, we denote these chained keys as kn to k0. Now suppose the server already knows k0 from the client. The client cannot use k0 as a password, but it knows k1. So it sends k1 to the server, and the server checks if hashing k1 once results in k0. Recall that this hashing is a one-way operation, which means that it's very hard to invert a hash. And this operation goes on for k2, etc. So the client now has two choices. Either store this whole hash chain in its memory, which is O of n storage cost and O of 1 computation cost, which is basically lookup operation in storage, or just store the seed kn and generate each required key on the fly, which is O of n computation. So in this way, we effectively trade off space for computation. However, there exists a work from 2002 by Jacobson, which provides an algorithm to achieve logarithmic storage and computation, which is great. So instead of storing or computing the whole hash chain, the algorithm considers those pebbles at positions 2 to the j, for j from 1 to log n. And this algorithm now provides a way to store log n keys, while only needing log n computation on average as the client traverses the chain. So now we have the necessary background. We describe our signature scheme we use in black box IoT. It is basically, again, the same hash chain, but now we don't consider the keys as passwords. Instead, for example, beginning from key 0, we say that key 0 is our one-time public key, and k1 is our one-time secret key. In this figure, we don't have two chains. It is still the same chain, but I just copied below to show this. Then after these two keys are used, the next public key and secret key pair would be k2 and k1, and so on and so forth. So at any point, there is a pair of keys ki and ki minus 1 on the chain, where ki is the secret key, and its hash, which is ki minus 1, is the public key. And now to see how it works, we first need to initialize a counter. Then for signing a message M, we read the value from the counter, compute the corresponding secret key using the pebbling algorithm we saw previously, generate the signature as the hash of the concatenation of the message and the public key I, combined with a one-time secret key, which is sent in the clear. Then increment the counter to move along the chain and to ensure that these keys are not reused next time. And now to verify the signature, the verifier, who knows just the initial public key, should check if by iteratively hashing the secret key results in that public key. Of course, in this step, the verifier might have kept a more recent public key, so there won't be a need to do many hashes. So typically, it will be just one hash. and then check if hashing the message along with public key I does indeed result into sigma 1. Now, given the pebbling algorithm, the signing cost for the signer is log n, the verification cost for the verifier is O1, and there is no need for a synchronization between them. Note that our scheme is not the first hash-based signature scheme. However, it is the first scheme that does not require clock synchronization between signer and verifier. And previous work either made such a synchronization assumption, which in our setting we consider too strong, or had constructions way less efficient. So now to showcase how this signing would work on a class 0 device, we made an implementation for a hash chain of length 2 to the 26, which we can assume it will be more than enough for the sensor's lifetime. Note that although all the sensor needs are those 26 pebble values, someone should generate the whole chain first. So we consider that this setup phase can happen during sensor manufacturing, and the powerful host can just preload them into its memory. Our implementation was done on Arduino Uno, which has only a 16 megahertz microcontroller and 2 kilobytes of static RAM, connected through Bluetooth to a Raspberry Pi 3, which plays the role of the aggregator. The reason we chose a Bluetooth connection is because we consider a short-range wireless connection, which is important for our threat model later. And practically having SHA-256 as the hash function, which is used widely today, we showed that the whole program, including the pebbles, can fit on just 1678 bytes, and the signing sensor data takes only around 15 milliseconds. In immediate comparison with our scheme is the commonly used ECDSA scheme, and our measurements for an energy-constrained device showed that it can support about 50 times more signing operations compared to ECDSA. The caveat here is that while our scheme is much more efficient to ECDSA, if the wireless connection between the sensor and aggregator is unreliable, and the sensor keeps transmitting signatures, and since we consider that the sensor only blindly transmits without receiving confirmations back, then the aggregator will need to catch up after a long period of outage, and this recovery step might be more expensive compared to ECDSA. And this happens because our scheme does not need any synchronization. So moving to the big picture of our system, in conjunction with Hyperledger Fabric, we consider the following elements. First, we have the blockchain and the membership service provider, MSP, which is a trusted party controlling participation in the higher levels of the system. Then the orderers, which are responsible for the consensus algorithm required for the blockchain. Then some local on-site administrators in the IoT application. Then a set of aggregators and a set of sensors which sign their collected data and transmit them to the aggregators. This set of sensors and aggregators together with the local administrator forms a device group which submits the data to the higher levels of the system, which in turn can accommodate multiple such groups. So focusing on the main functionalities of our system, we first have the case where a sensor joins a group, where it needs to generate the hash chain or have it preloaded in memory as we discussed. And all the administrator needs is the public key to register it with the aggregators. Then a sensor transmits its signed data as normal using our signature scheme, and one or more aggregators verify the data. The data is submitted to the orderers as a transaction to be packaged as a block and update the blockchain. And the blockchain is also used when a sensor needs to be transferred from one site to another. So all the aggregator needs to do is to take the most recent public key, encrypt it, and submit it to the blockchain. So the new parent aggregator can then decrypt it and resume the operation with the sensor. Before talking about security in the next slide, note here that when a sensor sends its signed data, the aggregators in the group should be aware to check for conflicting messages or signatures. This means that as the sensors broadcast wirelessly the data, if one aggregator somehow receives one message, a signature pair, and another receives a different pair, then this is an indication of a security issue. Okay, so to discuss about black box IoT security, it is ensured by the security of our signature scheme, plus the security properties of the blockchain. However, recall that our scheme sends the one-time private key in the clear, which might be a man-in-the-middle attack vector. For example, an attacker might intercept this broadcast, learn the one-time private key, and replace the whole signature with an arbitrary signature. However, given the architecture of our system, such an attack is very hard to launch, as the aggregators would raise an alarm if an attacker tried to intercept a signature between a specific sensor and aggregator. Therefore, it would be very hard for an attacker to simultaneously do this for all aggregators, especially given the short-range broadcast nature of our system. Also, the blockchain is an additional safeguard, which is immutable and tamper-proof, and any submitted inconsistencies, even if they were not detected in the aggregator level, they would be detected finally in the blockchain level. To summarize, we presented Black Box IoT, which is a blockchain-based approach for authenticating industrial IoT sensors, and is tailored even for the most constrained class of sensors. We described our novel signature scheme and how its setup phase can take place during manufacturing. For example, the manufacturer could provide the label on the sensor for the public key as a QR code. Then we include a comprehensive threat model, and we show our practical results on a real-world class 0 device. So that was our presentation, and thank you very much for watching.
Excellent. And Panos is here. So we have time for questions. There is a Slack thread that is open. And so if you would feel most comfortable doing that, you can use Slack. 34 people, I think, is actually manageable. So if someone would like to unmute and ask, that is okay as well. Okay, so maybe I will start with a question just to seed the group. So I thought it was very neat the way that you guys use this Pebble approach to sort of reduce the computation cost. Have you looked at just architectural optimizations that could reduce the cost, right? So you're talking about big O notation in terms of computation time for the keys there. But, that's different from real-time actual computational costs. And I was wondering if you had given any thought to that.
Just to understand the question, so because we have actually, implemented on such a device which has similar properties, similar constraints. So we showed that, we have this big O notation, which is, logarithmic, but we showed that the actual time it takes to sign for such a constrained sensor with only like 1,500 bytes of memory, all it needs is like 15 milliseconds. And we also compared with this DSA, which shows that we have like 50 times gain compared to a standard ECDSA signature. on this class of sensors. So yes, we do have the asymptotics like logarithmic computation, but we also have the the actual implementation, which shows how it is compared to a classic ECDSS enhancement.
Excellent, excellent, excellent. Is there another question? I am a little bit worried that folks are having trouble accessing or trouble with the login. Is that the? Let me make sure that, not the login, I'm sorry, that's unclear. Dong, are you able to unmute and ask a question? If I'm not asking you to ask one, but could you do that? Or Jesse, yeah. I'm just calling a name.
Yeah, can you hear me?
Yes, okay.
Okay.
Yes, go ahead. Go ahead, Tom.
Oh, sorry, I thought you want me to test.
Yes, okay, great, yeah. great. Thank you.
You're welcome.
Sorry, just wanted to make sure that we were doing okay on that.
Yeah, sure.
Is there another question? If not, Panos, I'm assuming you have the Slack open, and yes. So you can also see where I started a thread in general for questions here. And if others have questions, we can take it on to Slack at that time. Okay, all right. So we will start with our second presentation. Logan, are you on?
Yep, I'm here. Okay. I also did the pre-recorded video.
Pre-recorded, okay. So Ning, can you set that up? And by the way, thank you, Panos, for an excellent presentation. Thank you.
Thank you very much.
Okay. So Logan Blue is a fifth-year PhD student at the University of Florida, working with Dr. Patrick Traynor. The majority of his research has to do with practical security for voice-based systems. And today he's going to talk about ephemeral authorization for display-limited IoT devices.
Good morning. Today, I'd like to talk about the security of smart hubs. In recent years, smart hubs and smart speakers have become significantly more popular. This popularity stems from the fact that these devices allow us to interact with virtual assistants. These virtual assistants help us manage our own lives, help us stay organized, and help us interact with other smart devices nearby. For instance, in a given day, a smart speaker may help us to know when a certain venue opens, and then later to navigate to that venue. Once we've returned from our daily outing, these same smart speakers can be used to help us order dinner, and then help us to stream some of our favorite content to other nearby local smart devices, things like smart TVs or Chromecasts. To put it plainly, smart speakers and smart hubs, they're just useful, and that usefulness doesn't stop at our front doors. The usefulness of these devices has seen them deployed into new environments such as hotel rooms and rental cars. In both these cases, they're being deployed to help guests have a better overall experience. And they bring with them a whole host of new challenges and exciting new possibilities. Many of the new challenges they bring with them, however, are security risks and security challenges. Specifically, the security challenges that we want to talk about in this talk have to do with the new environments we're putting them into. Traditionally, smart speakers and smart hubs are put into permanent spaces, places like homes and living rooms. These sorts of spaces, they come with them long-term ownership and a fully private space. So that means that this device will be deployed for years at a time, and that you'll have full control over who actually has access to the space that this device is located in. In these temporary spaces, things like hotel rooms, they're short-term ownership. You'll only actually control the room for several days, and during that time frame, you'll only have a semi-private space. The hotel still has cleaning staff and maintenance staff who may need access to the actual room, and you yourself as the user can't control them whether or not they're coming in or not. This means that these two different environments need two different types of authorization for our smart speakers. Particularly our permanent spaces, the more traditional setups, they need one-time authorization that gives full broad authorization to the smart speaker for all associated accounts. In comparison, our temporal space, our temporary space, needs some sort of temporary authorization that's a little more granular, both in terms of what authorization it has access to, and also for how long it will be authorized to do things. But the trouble is, these smart speakers were designed with permanent ownership spaces in mind. They weren't designed for the new temporary spaces. And so some of the design decisions that have been made for smart speakers hinder our ability to deploy them in these new, exciting temporary spaces. For instance, these devices lack displays, which makes it harder to identify which device you're connecting to. If it's just connected to a Wi-Fi network, it makes it harder for that initial bootstrapping phase when you're trying to initially set up the device. In a device that's set up once every several years, that's an okay trade-off. But in a device that's going to be set up every several days, it becomes a major hindrance. Additionally, we need to address the elephant in the room. These devices currently are set up for long-term authorization, which just doesn't work in these temporary spaces. Finally, these devices have no context of where the user actually is. And that's not a problem in a private space where only people you authorize are in your own living room accessing this device. We can't make that assumption in these temporary spaces. In a hotel room, the cleaning staff could come in, and if I'm not present, the device shouldn't be authorized. So we need to build in some level of user location awareness into these devices. So with that, we'd like to present Lux, which is our framework for helping these smart speakers be deployed into these new exciting environments. It's specifically set up to deal with the aspects of temporal aspects of these new environments for places like hotels, shops, cars, rental cars, etc. Lux is built around 4 main requirements. The first of which is our easy first-time authorization. As I stated in the previous slide, these devices are going to be set up every couple of days. And so that what was once a 10 to 15 minute process to be set up by Google and Amazon's own documentation can't be 10 to 15 minutes. It needs to be several minutes. It needs to be easy. Second, we need to temporally and spatially bound the authorization of the device. If the user is not in the hotel room, or if they've left the hotel room permanently because they've checked out, the authorization of the device should be suspended during those phases. Finally, we want to go ahead and enforce the principle of least privilege. This is a device that we don't actually own or control for any long period of time, and so we want to give it as little privilege as possible. Finally, we hope that one day Lux will actually be deployed, and so we wanted to design this entire system with an eye towards deployability. That brings us onto Lux's mechanisms. Lux is based off of 2 main mechanisms, the first of which is our authorization protocols. We have our first authorization, which is the main bootstrapping phase, where we give the smart speaker the smallest amount of authorization we can. The second is the secondary authorization phase, where we can basically expand the smart speaker's authorization and its capabilities with time as the user requests more and more features. And finally, we have our authorization state machine. This is where we actually get that granularity in location and temporal aspects of our framework. Excuse me. Our second main mechanism is our automated co-presence detection. This is how we're going to be detecting whether or not the smartphone and the user are in the same location as the smart speaker. This is made up of 2 main phases, the first of which is the initial location signature creation, and the later is the verification of test signatures or new locations to see if these 2 devices are co-located. Before we move too much further into our actual pillars though, I want to talk about our participants. So first off, we have the user. This is the person who actually owns the accounts that are being accessed. This user has in their possession a smartphone that we will use as a proxy as a proxy for their general location. Next up, as what I hope to be obvious at this point in the talk, we have a smart speaker. This smart speaker will be deploying some form of virtual assistant, something like the Google Assistant or Alexa, and that will be run typically in the cloud on something known as a root service. And finally, our last set of participants are our secondary services. These are services that are not directly controlled by the root service, but still host tight integration onto the smart speaker. These are things like DoorDash, Netflix, Spotify, etc. Now, Lux will be built across these 3 devices, the smartphone, the smart speaker, and the root service. And conveniently enough, these 3 devices all have software that is built, maintained, and designed by the root service. So for instance, the smart speaker, if it was a Google Home, it would be running the Google Assistant, which would be running on Google's cloud services. And then on the smartphone, you could actually also have the Google Assistant running as well. So this means that across these 3 devices, we only need one company, one entity to actually be deploying any code in order to have our device deployed. To have Lux deployed. This helps us achieve D, or our deployability requirement from before. So that brings us to our first protocol. And our first protocol will be done is the initial bootstrapping phase. That'll be done when the user first arrives at, for example, the hotel room. When they walk in, they can simply request from the smart speaker that they want to start a visit. This will have the smart speaker send a network request to the root service and ask for an inter-device communication identifier, or IDC. This IDC request will be responded by the root service with an IDC, which is effectively a nonce, as well as the ID of the root service. Now, at this point, the user has just walked into the hotel room. They haven't necessarily configured Wi-Fi, and they haven't really identified which smart speaker they wish to actually interact with. They've just spoken to it. And at this point, we don't want the user to have to pick out from a list of Google Homes on like a Wi-Fi network, since Google Home 10 versus Google Home 23, they're not sure which one they're going to be necessarily connecting to. So at this point, it's important to note that the smartphone would also be running the same virtual assistant as a smart speaker. So it would also be responding to the command start visit. Instead of doing these network requests, the smartphone will instead pull up the viewfinder and prepare to receive a light-based message from the smart speaker. The smart speaker will use its notification LEDs to flash a series of lights, which the smartphone will record using its camera, and then decode in order to get this message. This light message contains the ID of the root service. It contains some channel information, as well as the IDC. This channel information is network information that the smartphone can later use to open up a network connection, a more traditional network connection, back to the smart speaker. The smartphone will then take that IDC and will send that IDC back to the root service. The root service will then use this IDC in order to logically match the smart speaker and the smartphone, authorizing the smartphone at this time. And then the root service will send to both the smart speaker and the smartphone the key KAB, as well as send an IDC accept message to the smartphone. This IDC accept message is important so that we can notify the user whether or not it succeeded or failed. And at this point, our first authorization protocol will have completed. Additionally, I'd like to note that the light channel, when we're actually performing that communication, you're directing the smartphone at the smart speaker itself. So you're actually selecting which device you want at that moment. You're indicating that the one that's flashing lights that's directly in front of me is the device I wish to authorize. So at this point, our first authorization helps us with 3 of our requirements. First, it makes for a much easier first-time authorization, as opposed to right now, according to Google and Amazon's own documentation, is a 10 to 15-minute process and involves multiple steps in your smartphone. Instead, this is a simple 2-word voice command and recording approximately 10-second video. Second, this helps us to enforce our principle of least privilege, since at this point, the root service has only authorized the smart speaker to handle requests that the root service would handle. So these are the same sort of requests you could, give to a smart speaker just sitting on the side of the road, assuming it was connected to Wi-Fi and all that good jazz. But yeah, so it has a small amount of privilege it can possibly have at this point. Finally, as for the reasons we talked about on the previous slide, this protocol helps us achieve deployability, since we're only using software that's controlled by one entity, in this case, Google or Amazon or Apple, etc. Finally, it's important to note that after this first authorization protocol has occurred, we will go ahead and the smartphone will go ahead and set up a network connection back to the smart speaker using the information it derived from channel info. We'll then go ahead and leverage that more traditional network communication channel in our secondary authorization protocol. So our secondary authorization protocol will be used when we need to authorize more features. So when the user makes a request for something that the smart speaker doesn't already have access to. So a new account, something like the first time you request Netflix or Spotify. So the smart speaker will send its voice command up to the root service as it would do normally. When the root service determines that it needs new authorization, it will send a challenge down to the smart speaker, which will contain an IDC as well as the ID of the service being authorized. The smart speaker will then use that traditional network connection to send over the IDC and the ID of the service being authorized to the mobile device. And then the smart speaker will take that and will send the IDC back up to the root service. The root service will do the same check as it did in the first authorization protocol, and will then note to itself that it needs to authorize the smart speaker for this new service. It will then send an IDC accept request to the smartphone, once again, so we can notify the user in case this failed, or that notify them that they succeeded in this. Then the root service will go ahead and fulfill the request of the smart speaker as it would normally, sending down, in this case, the link to the Netflix video you wish to watch. This secondary authorization protocol, it helps us with help enforce the principle of least privilege, since we're only ever authorizing one service at a time rather than everything in one go. However, none of those give us actually our granular temporal or spatial authorization needs. So to meet those, we go ahead and deploy our authorization states. Now we have three main states. We have active, suspended, and expired. The active state is when the smartphone and the user are co-located with the smart speaker, and when the smart speaker needs to actively be fulfilling queries. The suspended is where we wish to maintain that logical binding between the smartphone and the smart speaker, but we don't want to be authorized right now. This would be when the user has not necessarily checked out of the hotel, but just gone out for the day. And finally, the expired state is when we actually delete the token, and that's just generally for good security hygiene. So we can move through these different states in our protocol in 4 ways. The first of which is our keep alive. So if the authorization for the token is in the active state, the root service will be sending active keep alive messages to the smartphone. If the smartphone responds to the keep alive, then we'll just continue to stay in the active state. However, if it fails to respond, so if your phone is turned off, it loses signal, it falls off a 9th-story balcony and meets its terminal demise, whatever it happens to be, we'll go ahead and move you from the active state into the suspended state. This ensures that Lux will fail closed. So if the smartphone, for whatever reason, is no longer available, we make sure that we keep all of your accounts still safe. Our third figure here is demonstrating that the smartphone can update the authorization state to any state that it chooses, whether that be active, suspended, or expired. This could happen when you detect that you've arrived back in the hotel room, so you wish to move from the suspended state into the active state, or you detect that you've left the hotel room, so you would like to move from the active state to the suspended state. It's key to note that this is the only way for us to actually move back into the active state for the token. And finally, our fourth figure here demonstrates that after spending a certain amount of time in the suspended state, the token will automatically move into the expired state. This is reminiscent of when you leave the hotel and you've checked out. You don't have to actually tell Lux that you've left. Eventually, it will just expire that token, ensuring that in the future you're still safe and keeping up with good security hygiene. So that completes our first set of mechanisms, and we're going to go ahead and quickly move through our second set of mechanisms, the automated co-presence detection. Before we do that, however, we need to consider what we're going for here. The co-presence detection is meant to tell us when the smartphone and the smart speaker are in the same location. Now, there's multiple ways we could do this, and Lux can work with multiple different ways of doing this. However, we could use something like a short-range wireless communication, something like Wi-Fi or Bluetooth, or use a distance bounding protocol, something like ultra-wideband. However, both these have either shown vulnerabilities to already existing attacks or require additional hardware than what's already been deployed on the millions of already deployed devices. So instead, we choose to go ahead and do some environmental sensing, since that seems to be the most deployable at this time. If something better shows up in the future, Lux could easily adjust to use that instead. So, while sensing Wi-Fi, what we're going to do is during that first authorization protocol, when we're recording that light message, and the smartphone and the the smart speaker are effectively right on top of each other, we're going to go ahead and record down all Wi-Fi signals that we normally receive at this point. We're going to record down the SSIDs as well as the received signal strength, or RSS values, all nearby Wi-Fi. And then we're going to take those and we're going to collect them and we're going to use them to form a signature location, or a SIG lock. Something important to note about the SIG lock is that it can be seen as a probabilistic distribution. And I know we're being a little light on the details actually of what we did here, but that's mostly for time constraints. So I would recommend that if you're interested in how we actually specifically calculate SIG lock, to go ahead and go back and look at our paper. So once we've created our SIG lock during that initial authorization protocol, we can go ahead and test against that later down the road. So the smartphone will go ahead and continue to calculate these same exact calculations, recording SSIDs and RSSs, and calculating new SIG values, signature values. We'll call them SIG-Ts. What we'll do is we'll take these SIG-Ts and we'll quantify the dissimilarity between the SIG-T and the SIG lock using the Hellinger distance. Now, the Hellinger distance of 0 would indicate that we have the exact same probability distributions, and a SIG lock of 1 would say that these two sets are completely disjoint. So using that, we can go ahead and build a binary classifier, either you're co-located or you're not co-located, based off of the Hellinger distance. To do this, we set a threshold, and if the Hellinger distance for the current SIG-T versus the SIG lock we recorded for the smart speaker are within the bounds of our threshold, then we'll go ahead and say that we're co-located with the device, and we'll authorize the device, moving the token from the suspended state into the active state, or leaving it in the active state, and allowing the smart speaker to have authorization and fulfill requests. However, if the Hellinger distance is not within the bounds of our threshold, then we'll go ahead and say that these two devices are not co-located, and we'll leave or move the authorization token into the suspended state, not allowing the smart speaker to access any of our current accounts. We wanted to test how accurate this was, so in order to do that, we calculated 5 sig locks within several rooms, and then using those sig locks as our base value, we then proceeded to leave the room calculating sig t's and calculating their Hellinger distances as we went. Doing this for several rooms, for 3 rooms specifically, and following all these paths multiple times, we were able to generate the rate at which we were deauthorizing the device as we left. We found on average that it took less than 60 seconds to achieve full deauthorization for all of our rooms. And before anyone asks, this little backslide in this graph here, this comes from actually where the corridor doubled back on itself, and we actually started walking towards the room we were leaving. So we have some level of we have a fairly high level of accuracy within this technique. So we found overall that we deauthorized when we were approximately 75 meters away from the smart speaker itself. And then we went on to do some additional adversarial testing and found that on average, we needed about 6 adversarial APs or access points in order to impersonate one of our rooms. What this means for an adversary is that the adversary would have to actually deploy 6 different access points in order to make any one room look like a different room. We go into this a little more nuanced, and this is a little more of a deeper conversation. So I recommend, if you're curious about what exactly we did and what this all means, I tell you to go ahead and go back and once again, look at our paper. So finally, we can briefly talk about our takeaways. We've designed our framework Lux, which is meant to fundamentally help smart speakers deal with the new challenges that they'll face in temporary deployment environments where the users will only be there for short periods of time, not the traditional long periods of time they're used to in their current deployments. Lux only relies on a single entity, the root service, in order to actually be deployed. So assuming we can get one entity such as Google or Apple or Amazon on board with this, we can easily deploy this without any additional help from every other service they support. Finally, Lux provides us with temporal and spatial bounds of authorization, allowing the smart speaker to be aware of when the user comes and goes and provide a higher granularity to our actual authorization. Finally, I'd just like to point out that the image here on the right is actually our testing rig we set up just to make our lives a little bit easier while recording hundreds of light messages. So that basically wraps up what I have for you guys today. Like the image says, if you have questions, I probably have answers. Once again, my name has been Logan Blue, and thank you all for listening, and I'd love to take your questions.
Cute picture.
Thanks.
I definitely have several questions, but I will give the audience a chance if anybody wants to either send me a private question or unmute.
So I know you were talking about everything kind of relies on the root service having a single root service for phone and smart speaker. So how would this work, say, if you don't necessarily have that assumption, where you can't assume that everything is in the same ecosystem? Because a lot of times you might have somebody with an iPhone, but then the hotel has this Google Home installed. Then what do you do?
So in that case, you would need the person with the iPhone to basically have the Google Assistant app running on their phone. So it would be very hard to break the logical link between the smart speaker and the root service. And the nice thing about your phone is you as the user, you actually control it. So if you were to show up somewhere with an iPhone and they have Google Home deployed, you could, assuming that Apple offers it on the App Store, download the Google Assistant, and then this would still continue to work as we've laid out.
Okay, so the idea is you just have to adapt to, you have to pick your root service to match the device that's installed that you're trying to authenticate.
Yeah.
Okay.
So the other thing with this is a lot of this is meant to help people who have these deployments at home. So if you, for instance, had a Google Home at home, when you went to a hotel, if it also had a Google Home, you'd want that to act just like it did in your house, right? So if you don't necessarily live with a smart speaker, this might not necessarily be as helpful to you, but you can still very well hold a Google account with lots of things linked to it for when you travel.
Okay, that makes sense. And I think actually that clarification that the idea is you're taking your home setup and taking it with you on the go, that I think helps clarify a lot too. Thank you.
Yeah.
Go ahead, Dom.
Yeah, actually, I have one question here. Thank you for your talk. So did you actually consider? I'm wondering whether the background processes on this kind of devices you have here are already installed apps, maybe user interactions. For example, you try to do something while users using it. Will that affect your proposed technique here?
Sorry, can you rephrase that? I don't quite follow your question.
Yeah, so do you have an assumption about this kind of services already loaded on the IoT devices? For example, if users are using the IoT devices for that point, for example, playing some video or something else, and you propose something right here, and then my question is that it will be that like pre-installed apps or maybe user interaction processes in the backend will affect your approach here.
So are you saying effectively if you were using the smart speaker for something else, and then you tried to make a new request? So from the smart speaker's point of view, it's just like if you're using one of these devices for something now. So if you're, let's say, streaming Spotify on it, and then you ask it to do some other command, Spotify can continue playing on it, since all we're going to necessarily have to do is that same network connection that we're already doing. So you'd be theoretically hitting the secondary authorization mechanism, right? So that secondary protocol, and that behaves just like how these smart speakers currently respond to commands. So if your new command wouldn't interrupt the previous, whatever you were doing, whatever action's currently occurring, I don't see a reason why we couldn't continue to do the exact same operations. Does that make sense?
Yeah. Okay. Thank you.
Okay. Yeah.
Right. Thanks.
So Logan, I have maybe actually a long sequence of questions, but I think the most important clarification is, you mentioned this example where you have hotel staff coming in and out of the room. Is it possible for the hotel staff and a user, a client of the hotel, to interact with the speaker at the same time? Oh, interleaving between authorizations? That wasn't clear.
So I think what you're getting at here is effectively you, the user, are either in the room or have just left the room, and a staff comes in behind you and attempts to continue using your services. So if you remember that.
No. Actually, I want to know if they could use their own services, if they could log into their own services while this is happening.
Yeah. So I believe we discussed this in the paper. So the smart speaker could effectively hold multiple. So we didn't talk about it in the presentation, but in the paper we discussed that we're effectively using the TLS connection as a unique identifier, right? So when you arrive and you place basically place a command, we can figure out which identifier you need to be using, right? So since we have these active and expired states, if let's say that two users both arrive, both of their tokens could be in the expired state. And while we haven't explicitly had a mechanism to basically say this one is this one and this one is this one, right? So this command came from speaker A or person A, and we want to use their account. There's no reason why this would get in the way of that sort of command, that sort of system. So on a lot of these smart speakers now, they're doing some sort of speaker recognition. So you could still have that layer of speaker recognition and use that to basically say, I'm dealing with speaker A, and speaker A is currently authorized, so go ahead and use their accounts. And then speaker B goes in and talks, and we do that same level of speaker identification and say that, okay, speaker B is not currently, or sorry, if speaker B was present. So yes, you could have two people using two separate accounts, as long as you had some way of aligning which voice with which set of accounts.
I see. That's fascinating. So I guess my more general question then is, at the end of the day, it feels like a virtualization problem, right? It feels like things that we've addressed in, for instance, infrastructure as a service and cloud computing, right? How do you have this remote resource that you want to provide authorization to, and how do you have multiple users for? Maybe at a high level, can you offer like an intellectual distinction between these things? Is there a major intellectual distinction, or is it just adapting the protocols to the resource constrained environment?
So there's a couple of major concerns that we have. So in the virtualization instance where I want to have multiple people using the same hardware, right? I don't necessarily care about the temporal or the space aspect of it, right? So when you show up to a terminal, you wish to log in, you're going to use that. But when you leave, you're going to log out or lock the device typically, right? Whereas in our case, we need that to be an automatic detection sort of thing, right? As you leave, we need to make sure that we pull that authorization. But since this is a device you're likely to come back to multiple times, we want to make sure that that was both fluid and automatic, but we also needed to help specify which device it was. So there's a lot of this that is borrowed from virtualization, and I would definitely agree with that. But I would definitely say there's parts of this that are a little more nuanced that aren't handled in classical virtualization concepts.
Okay, maybe one last one that I have, tangential to the things that I just asked you. When you were talking about proximity sensing, it seemed like there's a presumption that the microphone on the phone is available, and thus also the microphone on the speaker is available, which works well for speaker phone. But I think you were trying to generalize. So you could imagine a camera, or even better, an infrared sensor that somehow I would like to access and somehow interact with, right?
Okay.
Any idea on how you would sort of do this proximal sensing when you have different types of sensors involved?
Yeah, so we only use the microphone on the smartphone during that first initialization phase, that first bootstrapping. In theory, we didn't actually have to have that. You just need some way of triggering the fact that this phone is near this smartphone is near a smart hub, and that we're wishing to authorize to it. So in theory, if you had a secondary sensor of some kind on the phone, whether that be like, I have a Pixel 3, so I have like the squeeze sensor, or if the smart speaker had the ability to communicate to the phone in some other like near field communication, right? So like I'll send out a specific broadcast, on Bluetooth, to where like Bluetooth Low Energy would be a great example. So if your smart speaker had Bluetooth Low Energy into it, it could send out a broadcast that, hey, I'm starting a visit message. Any smart speaker nearby or any smartphone nearby who's also running this protocol, go ahead and launch yourself into the application. We did it just since we use microphones, since that just seems to be the simplest point to point with the most already deployed hardware.
Awesome. Any other questions for Logan? I'm checking the Slack at the same time, but I am not seeing anything on the Slack. Okay, so our first session, I guess we started 2 minutes early and we're ending about 5 minutes early, so this is perfect, well timed. Thank you everybody for attending session 1. Session 2, privacy, is up next, and is the chair, is that? Double check who that should be.
I'm here, yeah.
Yes.
Hi,
okay, thank you.
Thank you.
Yeah, I thought it was you, Dong, but I wanted to make sure. So Dong will soon change his name to session chair, and will the presenters please contact Dong. And thank you to our presenters, and we'll see you in GatherTown.
Thank you.
Hello, everyone. Good afternoon. Thank you for joining the IoTDI 2021 session 2. So our session now is privacy. So I'm Dong Chen. I'm assistant professor in FIU. So it's my great pleasure here to introduce to you two very outstanding research work in this session. So the first work is from Duke University. So Ali is Ali is a third-year PhD student at Duke University. His advisor is Professor Yiran Chen, and his primary research area focuses on federated machine learning, privacy, IoT, and edge computing system. So now first, let's welcome Ali to present his work. Ali has chosen to use his recorded video. So can we play the video now? Thank you.
Hi everyone, my name is Ali. I'm a PhD student from Duke University. Today, I'm very honored to present our work, Deep Obfuscator, obfuscating intermediate representations with privacy-preserving adversarial learning on smartphones. This is a joint work with Tsinghua University and the Royal Melbourne Institute of Technology. First, let me briefly introduce the background, motivation, and the high-level idea of our work. Recently, deep learning has been widely applied into many mobile applications, such as image recognition, machine translation, video streaming, and so on and so forth. However, running deep learning models on mobile devices is technically challenging due to limited computing resources and power budgets. Many large-sized deep learning-based applications are often deployed on cloud servers, such as machine learning as a service. These cloud-based services require users to send data to the cloud service provider. However, this requirement may raise users' concerns about privacy leakage, since various private information may be contained in the images and other raw data. One widely adopted solution to address this privacy issue is to upload only extracted features rather than the raw data. Unfortunately, the extract features still contain rich information which can breach users' privacy. Specifically, as the top figure shows, an attacker can exploit the eavesdropped features to reconstruct the raw image, and hence the identity of the person on the raw image can be discovered from the reconstructed image. In addition, the extract features can also be exploited by an attacker to infer private attributes, such as gender, age, etc. Such adversary models can be trained by an attacker through continuously querying the cloud service to collect the eavesdropped features as inputs, and the ground truth of the queried data can be used as labels. There are a few studies have been performed to defend against the reconstruction attacks and prevent private attribute leakage. However, none of these studies has investigated whether defending against the only reconstruction attack or private attribute leakage is sufficient to prevent either or both types of attacks. Our experiments demonstrate defending only reconstruction attack cannot prevent private attribute leakage, and vice versa. For example, the bottom figure shows two examples of reconstructed images when we defend against only either the reconstruction attack or private attribute leakage. The column A shows the raw images, and the column B displays the reconstructed images when we defend only private attribute leakage. These reconstructed images still contain many details of the raw images, and allow an attacker to re-identify the person in the images. The reconstructed images when defending against the only reconstruction attack are shown in the column C. Although almost all distinguishable information has been masked, we can still achieve a 94% accuracy in detecting the gender of the person in the reconstructed images. In this work, we propose deep obfuscator, an adversarial training framework to learn an obfuscator that can hide sensitive information, which can be exploited for reconstructing raw images and inferring private attributes, and still keep useful features for image classifications. Although we focus on image classifications in this paper, Deep Obfuscator can be easily extended to many other data modalities, such as text data. We also conducted the case study on the text data in our evaluations. Next, I will introduce the design of Deep Obfuscator. As the figure shows, Deep Obfuscator consists of 4 modules: obfuscator, classifier, adversary constructor, and the adversary classifier. The key idea is to apply adversarial training for maximizing the reconstruction error of the adversary reconstructor and the classification error of the adversary classifier, but minimizing the classification error of the intended classifier. The obfuscator is a typical encoder which consists of an input layer, multiple convolutional layers, max pooling layers, and batch normalization layers. The obfuscator is trained to hide privacy-related information while returning useful information for intended classification tasks. The performance of the classifier is measured using the cross-entropy loss function. The classifier is jointly trained with the obfuscator as a complete CNN model, where theta O and theta C are the parameters of the obfuscator and the classifier. A service provider can choose any neural network architecture for the classifier based on the task requirements and the available computing resources. By continuously querying the cloud service, an attacker can train the adversary classifier using the eavesdropped features as inputs and the interested private attributes as labels. Similar to the classifier, the performance of the adversary classifier is also measured using the cross-entropy loss function. When we simulate an attacker who tries to enhance the accuracy of the adversary classifier as high as possible, the adversary classifier needs to be optimized by minimizing the loss function here. On the contrary, when defending against the private attribute leakage, we train the obfuscator in order to degrade the performance of the adversary classifier while improving the accuracy of the classifier. Therefore, the obfuscator can be trained using the bottom objective function, where lambda1 is a trade-off parameter. The adversary reconstructor, which is trained to recover the raw image from the eavesdropped features, also plays an attacker role. When playing as an attacker, the adversary reconstructor is trained to optimize the quality of the reconstructed image, as close as the original one. In this work, we leverage MS-SSIM to evaluate the performance of the adversary reconstructor. The MS-SSIM value ranges between 0 and 1. The higher the value is, the more perceptual similarity can be found between the two compared images, indicating a better quality of the reconstructed image in this case. Consequently, an attacker can optimize the adversary reconstructor based on the loss function. On the contrary, a defender expects to degrade the quality of the reconstructed image as much as possible. To this end, we generate one additional Gaussian noisy image. The adversary reconstructor is trained to make each reconstructed image similar to the noisy image, but different from the original image. And the performance of the classifier should be maintained. When playing as a defender, the obfuscator can be trained according to the objective function in the bottom. Based on the defined optimization problems, the obfuscator can be learned through the adversarial training. We recommend audience to find more details about the training process in our paper. Next, I will show you some key evaluation results. We implement Deep Obfuscator with PyTorch and train it on a server with 4 NVIDIA GPUs. We adopt Celib A and LFW, which are 2 benchmark face datasets for the training and testing of Deep Obfuscator. In addition, we compared our method with 4 privacy-preserving baselines, which have been widely applied in the literature. The first one is the noisy method. It perturbs the raw data by adding Gaussian noise. The DP method means applying the differential privacy, where we inject the Laplacian noise in the raw data. The encoder is a vanilla DNA-based encoder to learn latent representation, and it holds the same model architecture as our obfuscator. The hybrid method applies principal component analysis to extract features from the above encoder, and then add Laplacian noise to those compressed features. First, we perform an experiment to simulate a reconstruction attack using different reconstructor architectures. We adopt the reverse of the obfuscator as the adversary reconstructor during the training. However, an attacker may not be able to know the architecture of the obfuscator, and hence, the attacker may conduct a brute force attack using the reconstructor with different architectures. Here, we implement 3 additional reconstructors as attackers in our experiments. We again adopt the MSSIM to evaluate the quality of the reconstructed images that are generated by each reconstructor. The results in the top table show that although we apply the mirrored obfuscator architecture for the adversary reconstructor when training the obfuscator, the trained obfuscator can effectively defend against the reconstruction attacks, no matter what kinds of architectures are adopted by an attacker in the reconstructor design. In addition to MSSIM, we also adopted the peak signal to noise ratio (PSNR) to evaluate the quality of the reconstructed images. The bottom table presents the average MSSIM and the PSNR on the testing data of the obfuscator and 2 baseline methods. The result shows that Deep Obfuscator is the most effective one to defend against the reconstruction attack, and the baseline method can hardly hide the privacy information from the features. And the figures at the right side show several examples of the reconstructed images. We also conduct an online human perceptual study to directly examine whether a person in a reconstructed image can be re-identified by humans. This study consists of 10 questions, each of which includes 1 reconstructed image and 4 raw images as options. One of the 4 options contains the person in the reconstructed image. Participants are instructed to choose the option that looks like the person the most in the reconstructed image. The figure here shows 1 example question in the survey. It's very difficult to find hints from the reconstructed image to identify the correct answer, which is figure D here. There are 40 participants involved in this survey, and each participant can only submit 1 response. Hence, we collect 40 responses in total in this study. The average re-identification accuracy of 10 questions is 28%, which is very close to a random guess, namely 25% for 4 options. Furthermore, we can imagine if there's no option offered to an attacker, it will be more challenging to re-identify the person from the reconstructed image alone. We also compare the utility privacy trade-off offered by Deep Obfuscator with 4 privacy-preserving baselines. In our experiments, we set gender and heavy makeup as the private attributes to protect in Celib A, and consider detecting smile and high cheekbone as intended classification tasks to evaluate the utility. With regard to LFW, we set gender and Asian as private labels and choose recognizing black hair and eyeglass as intended classification tasks. Note that the evaluation metric of privacy is defined as the classification accuracy of private attributes that we aim to protect, and hence, the lower accuracy of private attributes indicates a better privacy protection. Therefore, the ideal case for the utility privacy trade-off should be in the lower right corner, which represents achieving the maximized utility while offering the strongest privacy protection. As the figure shows, although deep obfuscator cannot always outperform the baselines in both utility and privacy, but it still achieves the best utility privacy trade-off under most experiment settings. We also conduct cross-dataset evaluations by training the obfuscator using either CLIB-A or LFW dataset and test the performance on the other dataset. Specifically, we choose recognizing black hair as the intended classification and gender as a private attribute that an attacker aims to infer from the obfuscated features. As the table here shows, the obfuscator that is trained using one dataset can still effectively defend against the private attribute leakage on the other dataset, while maintaining the classification accuracy of the intended classification task. For example, if we train the obfuscator using CLIB-A and then test it on LFW, the accuracy of gender decreased to 53% compared with 57% by directly training the obfuscator using LFW. The accuracy of black hair marginally increases to 94.79% from 94.31%. The reason is that CLIB-A offers a larger number of training data so that the obfuscator can be trained for a better performance. In addition to evaluations on two benchmark datasets, we also conducted two case studies. First, we performed evaluations on multi-class tasks to verify the obfuscator's performance. In this case, we used a State Farm dataset, which consists of 10 different driver behaviors from 26 people. We consider driver behavior recognition as an intended classification task, while the driver's identity is a private attribute we want to protect. With our adversarial training method, the accuracy of driver behavior classification slightly drops from 98% to 95%, but the accuracy of the driver identity recognition decreased significantly from 99% to 30%. In addition, deep obfuscator can be easily extended to many other applications with various modalities of data. Here, we evaluate the deep obfuscator on Twitter AAE dataset, which is a large collection of tweets. In our experiment, binary mention detection is considered as an intended task, while the race is a binary private attribute we aim to protect. With applying deep obfuscator, the mention detection accuracy marginally drops from 81.69% to 81.38%. However, the accuracy of race classification decreases from 79% to 52%, which is a totally random guessing level. To conclude, in this paper, we proposed an adversarial training framework, deep obfuscator, to learn an obfuscator that can hide privacy-related information from intermediate representations. We have conducted extensive experiments on benchmark datasets demonstrate that deep obfuscator can simultaneously defend against both reconstruction attack and the private attribute leakage. And the transferability of deep obfuscator shows the great applicability in the real world. Thank you for your attention. Please feel free to contact us if you have any question. Thank you.
All right, thank you. It's very good talk. So do we have any questions from the audience? You can leave your question in the chat box, also on the Slack channel, or you can unmute yourself to ask your question. Okay, so I didn't see a question from the Slack channel. So, okay, so actually I do have two questions here. I think, hi.
Hi.
Yeah, I think my first question is that you talk about this kind of privacy information leakage.
Yeah.
Who in the practice, right? Who actually could be the potential, adversaries, like attackers in your system?
So yeah, that's a good question.
Right.
So for the threat model in our proposed work, we consider the adversary could be two types of the adversaries. So one is the the real attackers which can reside between in the communication channel between the the clients and the service provider in the cloud. And another case could be the some administrators inside the cloud service provider. So they may intentionally or unintentionally perform some malicious behavior and influence on the user data. So that's the threat model we consider in our work.
Okay, got it. So basically consider two parts.
Right.
The inside one, outside. Outside
right.
is on the path from the user to the cloud, right?
Right.
Path adversaries. Yeah. Okay.
Yeah.
Thank you. I think if there are no more questions, I have another question here actually.
Yeah. Sure.
Sure. When you talk about when you do the evaluation.
Yeah.
So for this kind of adversaries, right? So
yeah.
Did you actually consider like adaptive adversaries in this project now? For example, I'm talking about, when the some adversaries on pass, they may observe, they may monitor your system, right? Defending system a little bit, and they learn some knowledge about your privacy preserving technique.
Yeah.
Would they be able to learn something from it? Did you consider that part of your project for now?
Yes, that's actually a great question. But yes, the answer is yes. So the attacker can definitely design a more sophisticated attack method. So which means we can observe the the feedback or the prediction result from the cloud service provider, and they can adjust either the architecture or the training method to get a better performance on the private attribute inference. But in the country, the defender can also design adaptive defense techniques. We can periodically or some for a while we can retrain our obfuscator, or we can fine-tune the obfuscator to in order to improve the our privacy protection effectiveness. Yeah, I think that will happen in the real world, but I think that's the game between the attacker and the defender. It's really hard who can guarantee the success between them.
Yeah. Okay, got it. Thank you for the clarification. Yeah, I think that would be very interesting to see actually how your system can respond, this kind of whatever accuracy you present here, how that actually can respond to the new challenges actually, raised up by the vary with the time, right? So the attacker can learn a little bit about it, like adaptive attack model or something like that, maybe. Yeah. I think that's interesting. Yeah,
that's an interesting point.
Right. Thank you. Yeah, thank you. Very good work. Do we have more questions before we go to the next paper? Let me see here. There are questions here actually.
Yeah.
First question is, what's the noisy approach with Gaussian noise you compare against with satisfying difference of privacy as well? This is from Mohan. Yeah.
So basically the question was a noise approach with Gaussian noise you compare against the satisfying differential privacy as well. So for the Gaussian noise, for the baseline, applying the Gaussian noise, we didn't guarantee this method achieve the differential privacy. We just inject a random noise in the raw data. So there's no guarantee for the differential privacy. But actually we do have a DP method which can with a deep differential privacy guarantee as another baseline in our evaluation. Yeah.
Okay. Yeah, thank you. And then we have another question from Omid. So can the addition of probabilities noise to the images safeguard against more sophisticated attackers? Yeah, so that's actually a question about attacker. Yes.
Yes, so that's a good question. So in terms of the private attribute leakage, we can definitely design a more sophisticated noise injection mechanism. But for defending against the reconstruction attack, based on our current experiments, we haven't seen a good method by just simply injecting the noise can totally, prevent the attackers from reconstructing the raw data. So that's why we design, you see in our design, we have two additional branches. So the one branch is to defend against the reconstruction attack. So the other one is to, defend to prevent the private attribute leakage. So the answer is if we just inject the probabilistic noise, we can improve the defense for the private attribute leakage, but we cannot guarantee the defense against the reconstruction attack. Yeah.
Okay. Thanks for the clarification.
Yeah.
Do we have more questions? Let me check the Slack channel again. So, thank you.
Thank you.
Yeah, we'll move on to the next paper. Actually, the next paper is obscure night. It's a learning attribute invariant latent representation for anonymizing sensor data. So it's talking about privacy preserving on sensor data. So this work is presented by Omid, which is who actually from University of Alberta. So he is a, sorry, just give me a second. Actually, he received his, Omid received his master's degree from the University of Alberta under the supervision of Dr. Omid Adakanin and Dr. Hazy Casey. He has published many articles in machine learning, artificial intelligence, and high-performance computing, all with a background and focus on security and privacy. So Omid has already uploaded a pre-recorded video, and I think Omid already choose to play the video. Yeah, please help us set up the video. Thank you.
Hello everyone, my name is Omid Ajasani. Today I'm going to present to you my paper entitled ObscureNet Learning Attribute Invariant Latent Representation for Anonymizing Sensor Data. This is a joint work with my supervisor, Dr. Omid Adakanian and Dr. Hamza Khazai. In this slide, we can see two articles discussing the privacy concerns of IoT device users requiring new privacy preserving techniques to be added to their IoT devices. One is the privacy concerns regarding the usage of annotated voice recordings in the training of Alexa, and the other is with the addition of a new sleep tracking feature to Google's Nest Hub. The issue is that IoT and mobile applications are collecting users' data to deliver tailored services to their customers. However, the main privacy concern is that alongside with the non-sensitive and useful public attributes collected for training of new neural networks, also privacy sensitive information are collected. This information might include the age, gender, and health information of the users. The previous techniques that included the all or nothing approach wouldn't be applicable to the IoT data collection process, and we need new anonymization techniques. The recent sentiments towards IoT devices was that for us to benefit from the free services provided by IoT developers and companies, we need to give up a bit of our privacy, and IoT companies have learned different ways to monetize the collected data from the users. They would collect the user data in cloud infrastructure, aggregate and analyze it, and sell the analytics to the advertisement companies to make profits. We as customers would require anonymization techniques that would limit our privacy loss while we are using the services provided as free. There has been extensive research already done in this area. These include low-level anonymization techniques, including access control and terrestrial execution environments, differential privacy and k-anonymization mechanisms that provided plausible deniability to data owners within datasets, machine learning-based techniques, including autoencoders and adversarial training, for example, AAE, or the anonymization autoencoder and the replacement autoencoder from the Malikzadeh et al. And last but not least, federated and distributed learning techniques, including techniques that reduce and eliminate the need for centrally collected data for the training of the neural network models. However, there has been a gap within the anonymization techniques from the related literature. With the techniques that rely on algorithmic techniques, for example, the differential privacy techniques, the issue is that they do not address the utility privacy trade-off, and also they do not stop intrusive inferences from the collected data. And the model-based techniques, due to their deterministic nature, fall prey to the re-identification attack that we are going to later introduce in this presentation. The public and private attributes are entangled, and this would make the anonymization of the sensor data collected from IoT devices a really difficult task. And the reason is that due to the public and private attributes and the patterns that identify and are used to infer the public and private attributes from the time series data being entangled together, by removing one, you will directly affect the other. And by removing the patterns that indicate the private attributes of the data, you are also removing the usefulness of the data and affecting the usefulness of the data. And in this presentation, we are going to look into a way which helps us keep the public attribute while we are getting rid of the private attributes of the data. The outline of this presentation is as follows. First, we are going to introduce obscureness and the CVAE, or the conditional variational autoencoder framework that it is based on. Later on, we are going to see how adversarial training is going to boost the performance of the obscurenet technique. We're going to talk about the deterministic results and how we can navigate the utility privacy trade-off for the obscurenet. Later on, we are going to discuss different ways to mitigate the re-identification attack through non-deterministic modification mechanisms. We are going to see whether real-time on-edge anonymization is possible with obscurenet, and then we are going to conclude the paper with final remarks. As the architecture of the obscurenet goes, our goal is to learn latent representations and then modify them in order to anonymize the original data and reconstruct the anonymized version of the data through the conditional variational autoencoder framework. Here we can see that from the time series data and sensor data, we are creating embeddings, and we send the embeddings to the obscurenet. In the obscurenet, we have classifiers that are used to infer the private and the public attribute of the data. We use encoder in order to get the corresponding latent representation of the original unanonymized data embedding, and use the modified version of the private attribute alongside the latent representation, and pass it to the decoder to get the reconstructed version of the input data, which ideally would have the same public attribute with a different private attribute. Here we see the role of the condition variable in the CVA and our choice as the condition variable for the obscurenet CVA framework. We choose the private attribute of the data, y sub k, to be the condition variable of the data. And essentially, the condition variable in the CVA model introduces a structure into the learned latent variable space, and this helps us with the anonymization. Let's now see how the condition variable can be used in the anonymization of the obscurenet. First, we are going to train the obscurenet and get the CVAE that learns the representations and latent representations from the data with regard to the private attributes of the data itself. And then in the anonymization process, we are going to firstly infer the public and the private attribute of the data using the pre-trained classifiers, and then modify the private attribute through deterministic and non-deterministic ways. It is important that only 2 out of the 3 anonymization mechanisms in our case, and in the case of obscurenet, require pre-trained classifiers, and the randomized version wouldn't require pre-trained classifiers to do the anonymization because it's relying on random vectors instead of random manipulation of the vectors. And in the next step of the anonymization, after we get the latent representation and append it with the modified version of the private attribute, we are going to feed that to the decoder to get the reconstructed version of the data. However, in the empirical results and in our evaluations, we have seen that due to the information leakage about the private attributes into the latent representations, the condition variable's role in the decision-making about the private attribute of the reconstructed data is diminished, and it is not the sole decisive factor when it comes to selecting the private attribute of the reconstructed data. Hence, we want to limit the amount of information in the latent representations about the private attributes, and for that, we are going to use adversarial training. Now let's see how we are going to introduce the adversarial training and adversarial loss into the training of the CVAE framework for the obscurenet. Here we can see the original evidence lower boundary for the condition variation autoencoder having 2 terms, the KL divergence term and the log likelihood reconstruction term. The KL divergence term discusses the amount of disentanglement between the learned and approximated posterior distribution and the true posterior distribution. And also the other term discusses the log likelihood of probabilities of the reconstructed data given the condition variable and the latent representation. Now we are going to introduce the adversarial discriminator loss. So as we are going to reduce the amount of information about the private attribute Y in the latent representations, first we train a discriminator network which gauges the amount of information in the latent representations about the private attributes, and then we are going to train it adversarially in order to reduce and diminish the amount of information in the latent representations regarding the private attributes. Alongside the CVAE loss function, we are going to incorporate alpha and beta weights inside our adversarial loss function in order to be able to navigate the privacy utility trade-off in the anonymized data. Now we are going to look into ways that we are able to modify and manipulate the private attributes in the obscurenet technique. As you have seen and we discussed, for a given data embedding, we are going to infer the private and public attributes using the classifier network, and the encoder is used to obtain the learned latent representations. In the modifier module, for a given private attribute y sub k, in a deterministic case, it is always changed to another one, and in the probabilistic and non-deterministic case, it is changed either randomly to another one or is kept the same as itself, given a probability distribution and a random number. And then we are going to append the modified version of the private attribute to the obtained learned latent representations to get the modified version of the learned representation z prime sub k, which is going to be fed to the decoder to obtain the anonymized version of the original input data embedding. For our evaluations of the obscurenet, we are going to use 2 human activity recognition datasets. One is motion sense and the other is Mobiac dataset. These are time series datasets generated by the inertial measurement units. They have binary and non-binary labels useful for our evaluations, and different data attributes for activities, weight, age, and gender of the subjects in the dataset. Our anonymization task revolves around concealing the private attributes of the data, including the weight and the gender attribute of the subjects of the data, while keeping the activity inference accuracy as a measure of data utility as high as possible. Now let's see the results for the deterministic modification of the private attribute from the obscurenet while we are using the MOBIAC dataset and the gender attribute of the data subjects as the private attribute of the data. Here we see the inference accuracy for the activity, which is the public attribute, and the gender, which is a private attribute. We want the activity inference accuracy to be always high, and we want to reduce the inference accuracy of the gender private attribute to the lowest amount possible. We see the results for the original unanonymized data, about 97% for the gender inference accuracy. And we see the results for the anonymization from the anonymization autoencoder Malikzadeh et al. Work from the related literature, where it can successfully reduce the gender inference accuracy from 97% to 50%. After that, we are going to discuss our two baselines. One is the anonymization through the vanilla VAE and manipulation through the vanilla VAE, where it reduces the gender inference accuracy from 50% in the case of AAE to 21%. And obscurenet, which is our proposed methodology, which reduces it further to 14%, and while keeping the utility of the data as high as possible. We see the same trend when we are discussing the weight group and non-binary private attributes from the MOBIAC dataset. We see that AAE also reduces the private attribute inference accuracy to 57% while keeping the data utility as high as possible. And we further see that manipulations in our VAE baseline and obscurenet further reduce the inference accuracy of the weight group to 30% and 11.54%. Now let's see how we can investigate the utility privacy trade-off. We have seen that we have incorporated alpha and beta training weights in the adversarial loss function of the CVAE framework and obscurenet, and we are going to change and pick handful values for each and see whether we can navigate and change the amount of utility for the privacy and give one for the other for the sake of the usage and the use case. We have illustrated the results for the motion sense dataset, gender anonymization as a private attribute. We see a handful of weight options and values for beta and alpha. The x-axis and the values for beta are logarithmic, and the y-axis in the case of the left figure is exaggerated. We see the activity inference accuracy, which we want to keep as high as possible, and the gender inference accuracy, which we want to reduce as possible for different values of alpha and beta. Generally, if we fix the beta values, alpha values with smaller amounts fare better in the case of the higher activity inference accuracy and lower gender inference accuracy after anonymization. And also, if we keep the alpha parameter the same and fix that, mid-range values for beta seems like good options for better inference accuracy and lower gender inference accuracy. This only shows that we can navigate the utility privacy trade-off successfully, and the results are limited to the motion sense dataset, and the observations are only for the motion sense dataset. Now let's look at the non-deterministic modification through probabilistic anonymization. For a given data embedding y sub k, we see that it has this one-hot encoder representation and can be either probabilistically or changed to another private attribute or kept the same, or through the randomized version is changed to this random vector. And the difference is that by using this randomized version, we don't need a pre-trained classifier to infer the original private attribute. Now let's see the results for the deterministic probabilistic and randomized anonymization given different anonymization tasks from the motion sense to the MOBIAC gender and weight anonymization. We see the results for the random guess of the private attribute, and we see that both the probabilistic and randomized versions have results closer to the random guess, and the deterministic anonymization have the lowest and in some sense the better anonymization performance and inference accuracy for the private attribute. However, when being subjected to the re-identification attack, we see that the probabilistic mechanisms fare better compared to the deterministic one. And the reason is that the re-identification attack that we are going to introduce uses the anonymized version of the data alongside the known private and public attributes of the data in order to train a re-identification model, which is going to infer the private attribute of the data from the anonymized version of the data. And due to the deterministic nature of the deterministic mechanism of the obscurenet and the anonymization autoencoder work from the Malikzadeh et al. Related literature, we see that both of these work in case of different data sets fail and can be successfully re-identified, and their private attribute can be successfully re-identified using the re-identification attack. However, the re-identification attack cannot achieve the same high accuracy when it comes to anonymization through the probabilistic cases. Now let's see whether we can do real-time anonymization on edge using the Raspberry Pi 3 Model B. We are going to run ObscureNet on a Raspberry Pi 3 Model B to test the feasibility of real-time on-edge anonymization. We have observed that in the case of the motion sense dataset, every 200 milliseconds, one data embedding becomes available. And in the case of the Mobiac dataset, this number is 500 milliseconds, which is the time between each data embedding becoming available. Our results for the anonymization of one data embedding shows that it takes 2.9 milliseconds, roughly 3 milliseconds for the motion sense data set, one embedding from the motion sense data set to be anonymized by ObscureNet running on the Raspberry Pi 3. And it takes 30 milliseconds for one embedding from the Mobiac dataset to be anonymized by ObscureNet running on the Raspberry Pi 3 Model B, showing that within the time window that it takes one data embedding to be available, we can successfully anonymize the previous data embedding, and proving the fact that we can do real-time anonymization of sensor data on edge. Now let's look at the main takeaways of the presentation. We have introduced ObscureNet, which outperforms state-of-the-art generative methods when it comes to the time series anonymization of sensor data in the IoT applications. We saw that by changing the weight factors and introducing different weight factors in the adversarial loss function of the ObscureNet and CVAE, we can navigate the privacy utility trade-off in the anonymized data. And we saw that the probabilistic and randomized anonymization mechanisms proved to be more effective against the re-identification attack, where the deterministic modification and the baseline from the related literature, the anonymization autoencoder, fail against the re-identification attack. Thank you, and I will now take your questions.
All right, thank you. It's very good research work. So let's see whether we have questions from the audience first. See whether we have it in the chat box. Let me check the Slack channel. Okay. So actually, first I have a question here. Actually, it's very interesting work. So my first question is actually, so the story you built up here actually, that's actually very interesting. Actually, there's another domain like federated machine learning. Actually, it's very suitable to address the problem here. So my first question is actually, will your ObscureNet, right? This is a project, this architecture. Can you actually take away, make it adaptive to the federated machine learning, federated learning framework approach, such that user can actually use it in a smart home, like indoor environment, actually can apply your approach there. Is it possible to do that? Did you see any limitation or challenges there? Thank you.
So if I am mentioning the federated learning correctly, in the federated learning, you have this distributed way and paradigm of computing where the model is in some way trained on the local machine of the user and then aggregated in an anonymized way and in a privacy preserving way on the server to get the general model from the training on the different devices. So in this case, because we are not required to send our data to be stored publicly on the servers, it all comes down to the amount of trust that we have to the application that is running local training of the model. So if the users essentially trust the application or run their application in a trusted execution environment, for example, they have a tap on the data and where it goes. There are works like flow fence and works like chain tracking that reduce and minimize the amount of data moved from your device to a sink like a server or your network card. So if you can manage your data and you have trust to the application that it wouldn't run private inferences on your machine, you're safe to go. But if you can't do those, and the assumption is that nothing's essentially secure and private enough for us, then yes, after the data is collected, and given the fact that we deem our application running the anonymization of ObscureNet to be private and secure, we can essentially apply ObscureNet before the data is passed to the later third-party training, because the utility is high as possible. And the fact is that the utility and the inference for a model for the private attributes are kept fluid rather than deterministic in case of ObscureNet. So we intend ObscureNet to be general and for the reconstructed data to be used in a general way rather than a fixed application. So
Great.
I think,
yeah, thank you for the clarification. Yes, let's see whether we have more questions from the audience here. Let me see from the chat box. We don't have a from the Slack channel. Okay, so actually this is something require your clarification here. So when you talk about like testing on the Pi 3 or the other like prototype testing, so did you basically apply like a pre-trained model, right? You pre-train somewhere else and test. Okay, that's interesting. Yeah, so basically I see. So how do you think about the overload of the training process of your ObscureNet, this kind of pipeline? Do you think the overload is a little bit high? And my question is, can you actually train it on like a Pi? I think it's possible to do that. It's possible actually. Recently, there are a couple of things going on actually, like a tiny machine learning or something. I think probably, yeah. So I think my question is, how do you think about the overhead of your training process in the whole pipeline of ObscureNet? Yeah.
Yeah, so first of all, thanks to that person that mentioned a good job to me. So within ObscureNet, if you read the paper, and I highly encourage those that are interested in this work to go to the paper, because the presentation was a really watered down version of the paper. We had different baselines, like up to 5 baselines with all different autoencoder techniques. So please do refer to the paper if you're interested, and you'll find more and better detailed results there. So given the training on a local Raspberry Pi, we would be hurdled by 2 issues. One issue is that we want a global data set to be able to train it. If we go the federated learning way, it is possible, because each user trains the ObscureNet on its own machine and then sends the data and the intermediate model to the cloud to be aggregated and then passed back for the deployment. So that's one possible route. And also the ObscureNet itself might be harder and in some sense much deeper than a Raspberry Pi can train. To reduce that and to mitigate that issue, we have incorporated public attribute specific encoder and decoder. And through that and through making specialized versions of encoders for each public attribute rather than a general encoder and decoder, we achieved a very high order of reduction in our training weights for this ObscureNet approach to be able to run on a Raspberry Pi. So yeah, we have thought of a way to reduce the model weights.
Very good. Yeah, thank you for the clarification. So at this moment, if we don't have additional questions, So our session will end here, and let's thank you again. Thank you very much for the presentation from Ali and Omid. I think it's very good presentation, very good work. And next, we're gonna go to actually a break session, which is we will come back actually 20 minutes later. And next session will be part 2 security. It's still security session. It's session 2 actually, part 2, session 3, but it's the second part of the security whole session. So I will come back around 15 minutes. And thank you everyone for participation in this session. And wish you have a good day. Yeah, thanks.
And can I just chime in?
Sure.
Chin-Shi Chu is actually online now. So if you guys get a chance, please, the speakers for the next session, send your bio and information to Chin-Shi.
Thank you. See you.
Thank you, everyone. Take care.
Hi, this is Chen-Xi Qiu.
Thanks, Dong.
I think I already got the bio information from the speakers yesterday.
Oh, okay, cool.
Okay.
And thank you, Dong, for
I changed my name. I changed my name. Yeah.
Yes, I will change my name. Thank you for the reminder.
Change your name to the session there. Yeah, thank you. I see you soon. Yeah.
Okay, I think it's a time to start. So, good afternoon, everyone. Thank you for attending the session 3 of IoTDI, which is about security. So my name is Chen Xiqiu, and currently I'm an assistant professor at Rowan University. And it's my great pleasure to introduce the excellent researchers in this session to you. So as a reminder, we have 2 presentations in this session, and each speaker will have 20 minutes to introduce their papers, and 5 minutes for the audience to ask them questions. So our first speaker is Dr. Amit Kumar Sikder. So Dr. Sikder currently is a postdoc fellow at Georgia Tech, and he got his PhD degree from Florida International University in the last summer. And his research primarily focused on IoT and CPS security, with an emphasis on side channel attacks and application analysis. So let's welcome our first speaker. Hi, Amit, can you please share your screen?
Hey, all. Yeah, give me a second.
Sure.
Can you guys see the screen?
Yeah, I can see our screen. It's very clear to me.
Okay. Okay, so good afternoon, everyone, and welcome to IoTDI 2021. I'm Amit, and I finished my PhD from Florida University last summer. I was a member of a Cyber Physical Systems Security Lab. Today, I'm going to present our work titled as Sentinel, a robust intrusion detection system for IoT networks using kernel-level system information. So this is a collaboration work between Florida International University, Purdue University, and Penn State University, and I'm representing the Florida International University. This is the outline I'm going to follow for rest of the presentation. I will first explain the background and motivation of our work, along with the contributions. Then I will explain the technical details of Sentinel framework. Finally, I will explain the effectiveness of Sentinel in real-life IoT frameworks and conclude the presentation. So let's start. IoT has been a buzzword in recent years, and we see a exponential growth in IoT industry. In recent years, IoT industry has expanded rapidly, and by 2027, it will reach to a total worth of 1.4 trillion. Also, North America has seen a staggering 66% user penetration in the IoT domain in past couple of years. The concept of IoT started with simple trigger action phenomena between sensors and devices. However, modern IoT system offers app-based platforms like smartphone, and users can develop their own apps or download apps from third-party app markets. The figure in the right shows a common architecture of IoT network. It usually have a hub-centric design where the hubs communicate with different IoT devices connected through a common protocol. Also, IoT devices offer a device API to provide easy operation through a hub and customized apps. Finally, IoT environment have one or many user interfaces, usually smartphones or web apps for users to interact with the hub and devices and control the devices. This user-centric design and interoperability between IoT devices introduced several attacks in past couple of years. One of the most vicious IoT attack to date is the Mirai botnet attack. This attack performs several malicious activities in IoT network through a CNC server, and worst of all, Mirai botnet uses the victim device to identify other vulnerable devices to exfiltrate. While several existing work try to mitigate IoT attacks, the solutions are often costly and need customized approach. So this provides a motivation to find an effective intrusion detection system to tackle IoT attacks. Our initial investigation of IoT attacks revealed that the collection of low-level IoT device system information or kernel information can provide key insights into the behavior and goals of an attacker. Based on this observation, we proposed Sentinel, a robust intrusion detection system for IoT networks using kernel-level information. We designed Sentinel to be platform and protocol agnostic to support different IoT platforms and provide easy new device integration in a network. We implemented Sentinel in 2 different IoT platforms, that is WebThings and Home Assistant, and tested against 5 different IoT attacks. Sentinel achieves over 96% of accuracy and F-score, indicating effectiveness in real-life IoT network. For technical approach, first, I like to explain the threat model we considered for Sentinel. So in this work, we choose different attacks modeled from Mirai botnet, as this is the most common and diverse attack vector in IoT domain. We use several aspects of Mirai botnet attack in our threat model. Our first attack scenario is network scanning, where an attacker uses the infected device to scan nearby vulnerable devices in the network. Our second attack scenario is data exfiltration, where the infected device transfers sensitive data to the CNC server. Our third attack scenario is CNC keep alive, where the infected device occasionally communicate with the CNC server to keep the botnet alive and keep the attack ongoing all the time. For the fourth and fifth attack scenarios, we considered black and gray hole attack, which has the effect of small outbound traffic compared to large inbound traffic. For the gray hole attack, we also create partial packet drop to observe the effect of gray hole attack. Before we design Sentinel, we considered several design constraints, and we implemented that in the Sentinel's design. So our first design consideration is a Linux kernel. We used Linux kernel to get system level data. This is one of our observation also, because Linux is the leading operating system in IoT domain. We also considered hub connected IoT environment, which is common in different IoT platforms. We also selected MQTT broker for data collection process, which is a common cloud protocol that been used in IoT in different IoT platforms. For the constraints, we considered majority of the IoT devices as battery powered and have low computation power. Also, we considered IoT platform and protocol diversity in the design to provide a comprehensive detection system. So this is the overall architecture of Sentinel. It has 4 main modules. The first module is the kernel module, along with polling application, data collection application, and detection module. In the next few slides, I'm going to explain how each module works. So our first module is kernel module, which is used to export system and process level metrics. We used sysfs file system, which exposed different low-level information in the Linux system. Sentinel creates a set of entries for each corresponding matrix that is mappable with standard type. The metrics considered in Sentinel are shown in the table. In the right side of the table in the slide. We consider a total of 10 different metrics, including number of logical CPUs, frequency of each CPU, available RAM, and running processes, and so on. Our second module is polling application, which is a Python application connected to MQTT broker. The application periodically reads the kernel files and publishes the data to the broker. We used MQTT to send data to Sentinel's collection module, as it is quite ubiquitous in IoT platforms. Also, it offers dynamic polling rate that minimizes the overhead in the system. We'll see in the evaluation part of the slides how dynamic polling system works. The data collection module subscribes to MQTT broker and stores data to a PostgreSQL database. This provides us both local and remote access to the collected data. And the final module is the detection module, which provides both local and remote detection. We utilizes 5 different types of machine learning algorithms to detect malicious activities and sends notification to the user interface via hub. For the machine learning algorithm, we choose knife-based, rule-based learning, regression modeling, neural network, and tree-based classifiers. For testing the effectiveness of Sentinel, we implemented Sentinel in WebThings and Home Assistant IoT platforms. We selected a total of 9 types of devices and simulate the behavior using Raspberry Pi 4. For our data collection process, we consider 5 different attacks as mentioned in the threat model and collected data for different logical states of each IoT devices. We actually consider all the possible states for different devices while collecting the data. We selected 9 different devices. They are light bulbs, smoke detector, door lock, smart TV, thermostat, presence detector. Usually, like all the common IoT devices that we know. Each of our dataset is composed of 6,480 samples, and we used 75% of the collected data to train the machine learning models and 25% for testing, which is the standard industry practice. To evaluate the effectiveness of Sentinel, we choose several criteria. Our first evaluation criteria is to see how well Sentinel works against different attacks. So we consider both binary and multi-class classification in the evaluation. For binary classification, actually for both of the cases, we selected 7 different machine learning algorithms. For binary classification, from the table, we can observe that random forest and decision tree performs the best with accuracy and F-score over 96%. For WebThings, accuracy and F-score is over 96%, while Home Assistant, it drops to 94%. We can also see the decision tree takes less computation time than random forest classifier, which is a trade-off between decision tree and random forest while choosing the machine learning algorithm. For multi-class classification, we can see that Sentinel achieves highest accuracy to detect network scanning or pivoting attack, which was the first attack mentioned in the threat model. Also, the total false positive and false negative is below 2%. Another interesting fact that we see that random forest works better in Home Assistant while decision tree works better in WebThings. We keep this insight for our future work to explore more how the different machine learnings behaves in different IoT platforms. Our second evaluation criteria to observe the effect of machine learning model parameters on Sentinel. Here we can see the accuracy increases in decision tree classifiers with the number of trees. Also for random forest classifier, accuracy becomes almost constant for 8 trees. The computation time increases in random forest with the number of trees, which shows an interesting insight. This provides us the insight of accuracy versus computation time trade-off for random forest classifiers. So we can actually, while implementing Sentinel in the real-life network, one can actually consider what will be the best parameter for Sentinel to detect different attacks in real life. Our third criteria is to see the impact of platform configurations on Sentinel. From the figures, we can see that accuracy increase with the sampling frequency. Here we can see that the Sentinel achieves 95% of accuracy for 1 second of sampling rate, which drops to 90% for 10 seconds of sampling rate. So we can see that there is an inverse relation between the sampling rate and the accuracy of Sentinel. This is because when we increase the sampling rate to 10 seconds, we miss several data points and several behaviors of IoT devices that is crucial to detect the IoT attacks. For CPU cores, we can see that if the IoT devices have more computation power, like four cores, Sentinel works better with an accuracy of 95%. Our last evaluation criteria is to observe the performance overhead introduced by Sentinel. Here we can see that the power overhead is high with lower sampling rate. Also, highest power overhead is 10% for inactive and 8.3% for active devices for 1 second of sampling rate. This is an interesting. This is a very interesting insight that we found because it should the active devices should have more power consumption compared to the inactive devices. So we further investigated and found the major cause here that the most IoT devices actually go to sleep mode for inactivities, and it takes more power to turn it on by Sentinel to send the kernel level information. So for the inactive devices, it actually creates more power consumption than the active devices. We also see the effect of fixed and dynamic polling rate. For fixed polling rate, we can see that the fixed polling rate performs better while both options achieves accuracy over 91%. In conclusion, we propose Sentinel as a novel instrumentation system for IoT environment that uses kernel level information to detect malicious activities. Sentinel is a platform and protocol agnostic IDS which supports different IoT frameworks and needs little to no customization for new device addition. Our evaluation shows that Sentinel can detect different types of IoT attacks with high accuracy and F-scores in real-life IoT frameworks. As a future work, we'll study effect of adversarial attacks on Sentinel as Sentinel uses different machine learning algorithms to identify IoT attacks. So it will be really interesting to see how Sentinel performs on the effect of adversarial attacks. Also, we'll perform a detailed study to include real-life IoT devices behavior in Sentinel to identify the correct feature to improve the accuracy of Sentinel. These are some of the references mentioned in this presentation. We want to thank our National Science Foundation, U.S. Naval Research Office, and Cyber Florida for their support in this work. Thank you all for listening. And again, I'm Amit from Georgia Tech, and feel free to ask any questions. As I'm not the first author, I'll try my best to answer your questions. But if I cannot, I will follow up with those questions with my first author and let you know. Thank you.
Okay, thank you for the next presentation, Amit. And let's first see if there is any question from the audience. Okay, there is already one question in the chat box. So if there's a relationship between this Sentinel and the Microsoft Azure Sentinel, can you address this question?
It's just the similarity in the name.
Okay, it's very interesting. Okay, so if audience have any question, please feel free to unmute you and you can ask a question.
Excuse me, can you hear me?
Yes.
Yeah, I got a question. Could you please get back to the slide on the system design, which you have like four components?
Mm-hmm.
Yeah, thank you so much. So I'm kind of curious. I'm not entirely sure what is the polling part working. You say it's periodically read the kernel file and publish the data to the broker. Mm-hmm. So I'm curious about what is the exact kernel file or the information it's trying to give to the broker.
Okay, so whenever there's an activity going on, IoT devices actually write different kernel level information in the file system that we read from the polling application. So polling applications with a time interval, it actually reads all the file actually written and open when the IoT device is performing some activities, and put those data in the and publish those data to the MQTT broker that we actually collect from the data collection application. And then we actually segregate the data from data collection application for further training.
I see. So basically you are kinds of obtaining the information, the modifications on file system as a remark or proxy for activities So you can use that kind of
Yes.
data for further training. I see. And what was the modification on the kernel module, which is the number one component? You probably go one slide previous.
Oh yeah. So we actually sees the several metrics that actually expose. Like we see a lot of different metrics, but we ones because these are actually the features that we find interesting to see the IT attacks. Like whenever there's an attack, they target to change this number of these metrics. So our main observation was the the size of the RAM when there is an activities going on, the current memory used, the virtual memory used, and like 1, 5, and 15 minutes loads. These are mostly changed when there is an attack or an activity is going on. So you can actually see this in the training part that we can observe an attack and a normal activity based on those metrics.
I see. So basically, this metric is kind of the information that is getting pulled from the polling application and which are later exposed to your database.
Yes.
Okay. Okay. So one last question. So for commercialized IoT devices, if you would like to apply your system on it, that means you probably need to get access to their kernel and apply ingest what you have down here. Is that really possible? I mean, for most of the commercialized IoT device, I think they don't open source their software or
Yes.
even.
So yes, that's a drawback of this work. The commercial IoT devices doesn't have open kernels, but there are some open source devices that is actually allowing you to go to the kernel module. And if you use OpenHAB, there's some part of this metrics are always exposed. So OpenHAB platform has those like kernel modification feature, a little bit of that, not completely, but yes, it has for OpenHAB. But for others, it's little bit complicated. If you consider SmartThings platform, they actually completely closed source, so you cannot go to the kernel level.
I see.
Yeah.
Okay. Thank you so much.
Thank you.
That's a nice presentation. Thank you.
Okay, thank you. So any other questions from the audience?
Yeah, I have a question. First of all, thank you for your great presentation. Could you please go to the results slide?
This one?
The one that you talked about the power consumption.
Oh yeah, this one.
Yeah, here you provided one interesting and surprising result in terms of the idle devices. In some cases, you consume more power, more energy, and that is a little bit surprising for me. I really need to gain more information in this space, because there is another line of research that tries to understand how much the fingerprint of power usage of the IoT systems are the indication of an attack. And here, that is basically totally makes sense if there is more computation and there is something is working. I mean, an IoT device, when it's working, it consumes more power, more energy comparing with the time that it is in idle mode. So it is totally in contradictory to the other result that I have seen so far. So have you ever seen any other clues or other characteristics of these systems that show something totally in opposite to the other result of the other researchers? I mean, in terms of the amount of power usage based on the amount of computation, or when they are in idle mode. You mentioned that turning on or turning off, it pulls a lot of power, but I totally understand that part, but I would like to know more about the other characteristics that lead to this kind of result.
So the power consumption is actually for the Sentinel, like when we're collecting the data. So we have 9 different devices in our layout, and we plug and play different devices with different activities. We're trying to switch the logical states of them to mimic some of the activities going on in the IoT network. So the reason the power consumption is behaving like that here, because in the IoT network, when you have a large number of devices, not all the devices are active. So when we are collecting the data, it is trying to switch on all the devices all the time. So if a device is already active, it is just pulling the data from them. But if there is an ideal device, and we're trying to get the kernel level data, it is actually switching on again, and it is spiking the power consumption. So for attack behavior, like you can actually use this to see how different IoT attacks work. Or like there is an attack like never go to sleep. Like the attack actually tries the IoT devices to always make active to consume more power. So that can be mimicked from here. Like if you go details in here and see that most of the IoT devices actually being active, and Sentinel has with the polling rate, if you change that, the power consumption is spiking too much, you can come to a conclusion that some of the devices are already been infected, and you can go deep to other metrics and correlate that back to here.
I see. So one follow-up question here is that in this graph for the sample period 1 and 10, the idle inactive device actually pulls more power comparing with the other 3. So the main difference between these, what is the main difference between these samples and the other 3 samples that are in the middle, where active devices pulls more power?
So basically, when we increase the polling rate, it is actually when we're increasing the polling rate, it is getting data, less data from the system. So it's trying to get less power consumption from there. So it's basically we collected the data over like 4 hours period. Each data set is 4 hours. So when we collected the data, we changed the polling rate, and we see this observation over time. That whenever we're doing that, it's actually basically the different activities that are going on, and we miss some of the activities, and we actually couldn't see some of the activities that actually takes more power in the devices, that actually causing these changes. So basically, like the standard follow-up will be like this: that inactive devices usually takes more power for Sentinels, like whenever it is trying to get the data.
Okay, thank you so much.
Thank you.
Okay, so I think we are behind the schedule, so let's thank the first speaker. Okay, so so let's move to the next speaker. So the next speaker is the Dr. Renju Liu. So Renju, can you please go ahead and share your screen?
Yeah, sure. Thank you. So let me share my screen first.
Okay. Okay. So Dr. Liu is currently working at a tech company, and he obtained his PhD degree from UCLA in the last year. And during his PhD study, his main research area is about the IoT security. Okay, so please go ahead and start your presentation, Renju.
Okay, thank you for the introduction, and good afternoon, everyone. My name is Renju. I'm currently working at a tech company. And I just obtained my PhD degree last year from UCLA. So in this presentation, I'm going to present the work I did during my PhD. And the name is SecDeep, Securing the Performant Deep Learning Inferencing at the Edge. So we first look at like what kind of inferencing at the edge we're currently having. For example, we are using the face recognitions on the smartphone, and we are using the activity detections using our smart cameras. So this means that we basically have like all the software stack on top of our devices, like on edge. That's very close to us. So for example, the camera drivers, we will have some applications, some deep learning framework in the user space, and then we might have some other devices that are on our edge. And then what we will do is basically we'll perform whatever the inferencing and deliver such information to the user directly on our device. However, in this case, if let's say our framework or operating system gets compromised in the kernel space, then what will happen is that a malicious hacker might be able to obtain our sensitive information, and then what will happen is basically we will lose our whatever privacy information, or your image pictures, or like where you go, like whatever, everything. So we are going to basically prevent this from happening, even though our operating system gets compromised. So what this means is that we are going to provide the sensor data confidentiality. We are going to provide the deep learning inference code integrity, and then we need to have some reasonable inference latency, while even though the operating system gets compromised. So our threat model is that we do not trust like anything, even the operating system on the device. So to achieve all these three objectives, we are having some sort of options that we are going to use. So first of all, to achieve the isolation from the malicious operating system for the deep learning code, and as well as all other like the potential compromised sensors, we are going to utilize a trusted execution environment. For example, TrustZone is one of these popular execution environments right now we have. Then, in order to have a good performance, we have to think about like some other methods to basically accelerate our computing, because if we simply use a trusted execution environment, our performance might suffer. And then that's why we are thinking whether we could combine the neural networks on edge device with the trusted execution environment together to perform such like protections and the inference with a reasonable inference latencies. So if we look at these types of architecture, I think a strawman solution will immediately come up to us. That is that we simply put the deep learning libraries, including those drivers, into the trusted execution environment. Is this doable? The answer is no. Why? Because first of all, the lines of code are too large. We profiled like 5 different edge available deep learning inference libraries, such as TensorFlow Lite, Caffe2, PyTorch, Deep Learning 4J, and ARMNN. And we observed that the library size is too large. They all are more than like 100,000 lines of code, which means that we might actually increase our attack surface. Then second, our TEE, our trusted execution environment capability is not that much. It means that we do not have like a very large memories. However, if we put like everything inside the TEE, what we are going to face is that we might have very large memory usages if we enable the GPU acceleration. If you look at this figure, even though for some very lightweight like models such as SqueezeNet or even MobileNet V1, we will have like more than 100 megabytes of memory usage for the GPU acceleration, while the secure memory usually has only like a few megabytes. So to overcome like these two problems, basically we are thinking that we should have some TCB size reduction. where in this work, we require the deep learning code base to be split into two. So one is called a confidential computing base. So basically, these are the code base that requires the access to the plain text values of the tensor data. For example, the sensor data or some activation functions to actually compute the element in the different arrays. We're using like these types of raw data. And then we have another code base which we could be put outside of the trusted execution environment, or we call the non-confidential computing base. And this computing base does not require the access to the raw sensor data, but some other information such as the size of the data is needed if needed. For example, if we are configuring the GPU according to some tensor shapes, then we might put this kind of information outside of the confidential computing, outside of the trusted execution environment. So the reason why we are having these two is that we basically, for the code outside of the trusted execution environment, all the data might be exposed to the malicious attackers, but it's okay for them to see it. However, we will provide a way to protect them from modifying it. So that means that we need to provide some secure runtime inside of the trusted execution environment to just perform the duties I just said. For the code integrity, so we have to make sure that the code outside of the trusted execution environment cannot be maliciously modified. And then we also need to make sure that the data inside the trusted execution environment can be protected, but the data outside of the trusted execution environment is not needed to be protected in our design. So we are just designing this secure runtime in this work. So we have like two contributions, and then I'm going to discuss about like the first contribution. How do we protect the integrity of the non-confidential computing base? So that's where we design an integrity checker inside our secure runtime in this work. So this integrity checker composes like two parts. One is an offline preparation. So when we have identified the code that needs to be put inside the non-confidential computing base, we will modify the compiler to basically hash the code, and then we will need this hash information during the online protection to verify whether this code has been modified during this code loading into memory. And this is our online protection part. So for our online protection part, we basically use a secure boot, which means that we have a read-only kernel table, read-only kernel page table at the time when we boot our operating system. And then what we will do is we will basically, when there is a modification from like some registers, such as a page table register, that needs to modify the kernel page table, such information will be trapped into the trusted execution environment, where this trusted execution environment will ensure that this modification does not map to the memory regions of our secure buffer that are used to communicate with the trusted execution environment, and the code and the non-confidential computing base code, such that the code inside the non-confidential computing base code inside of the memory will not be modified just by any malicious checkers. So in our second part, we are going to have to provide some data confidentiality protections for our job. So basically, we are also having a data manager inside, we're having a data manager inside our secure runtime, and then we'll have an auxiliary data stack outside of trusted execution environment. So the job of this data manager is basically to sanitize those kind of tensor data where we use format preserving encryption. So, and this is the, let me explain like how we are actually doing this job with the performance optimization. So basically, let's say if we sanitize every single data, then we might encounter some performance issues. So in order to overcome that, we provide some optimizations where when there is a plain text tensor data, we first use format preserving encryption to encrypt it. We obtain the encrypted value. Then we store the value somewhere inside the TEE, where we have a hash map that maps the encrypted information directly to the plain text information, and then we deliver this encrypted value to the non-confidential computing base. So just to recap here, so our data manager will only provide the format preserving encryption. It does not change the format of the data, but it changes the value of the data, such that malicious hackers does not know like the value of the actual value of the data. So with these two major components, we can solve the issues when, like, if the trusted computing base size is too large, and then and as well as a TEE capability, where it means that our TEE has like only a few megabytes of memory. So in order to make the system, the whole architecture work, we also designed like several secure APIs that are used to communicate between these two components, the components that we provide in our SIGD. So we implement our work, we prototype our work in HiKey 960 using ARM Trust Zone with a ARM Mani G71 MP8 GPU, embedded GPU, and then we use Linux 4.9 as the untrusted environment. We use OPTE as the trusted execution environment. We evaluate our work on ARM-NN, which is a deep learning framework for ARM, and we evaluate our runtime. We modified the runtime for OPTE to basically host our trusted execution environment, and we run the experiment using the cafe model benchmark. We use like 3 types of models. So one is lightweight, where the model size is like a very small, and then medium weight, model size is not very small, then heavyweight, where the model size is quite heavy. And all these like light, medium, heavy are particularly for the edge devices, not for the desktop computers. And our results, we basically reduce the size for the ARM-NN TCB from 2000 to like only 1,000, roughly 1,000. And then our overhead, so we basically introduce like an extra overhead. If we are comparing with no secure directly with GPU acceleration, however, this is still faster than if there's no acceleration enabled in all of those models. And we also profiled our power consumption, and then we found that our work does not introduce like too much extra power comparing with the acceleration with GPU. But it actually saves a lot of power when there's no acceleration enabled on the edge devices. So that's all about this work. So if you guys have any questions, feel free to ask. Thank you.
Thank you, Renji. Very nice presentation. So first, let's check if there is any question from the audience. Okay, there's already one question. So on slide 10, could you please explain why the memory footprint increases with the GPU acceleration?
Okay, so this increases because the GPU acceleration will put the temporary data on the memory, and this is embedded GPU. So the GPU itself does not have memory. The GPU itself shares the memory with CPU. So with the intermediate data computed by GPU, they will be put on the memory and that's why it can be accelerated.
Okay, so does audience has any other question?
I'll ask a question, Shenxi.
Sure.
This is a really great talk. I think my question is very high level. I'm sure I'm missing something here. But how do you know that the encryption scheme that you use inside of the trusted execution environment isn't vulnerable to man-in-the-middle attacks by the operating system?
So, okay, so if I get the question correctly, you mean like, how do I know like the operating system will not be able to modify the data sent out from the trusted execution environment?
No, I think yes, you can start going down that path of answering the question that way. I think it seems to me like you're encrypting, but I don't understand why you're encrypting there. Because the operating system can observe everything, so it should be able to eventually infer your keys and decrypt.
Okay, yeah, so basically that's why we are adopting the format preserving encryption, and that's how like for example, your credit card is encrypted if you are using like a virtual credit card number, so which means that you will not see the real number, but we'll give you a virtual number. So this is one of our assumption that the format preserving encryption is secure enough to be, like attacked by the operating system to, like to obtain a key by the operating system. But certainly, if there's a side channel attacks on this, then some information might be leaked, but that's outside of the scope of this paper.
I see. I guess the reason why I asked the question, I guess that's very reasonable and that makes sense. But maybe harking back to our talk earlier today, where we were talking about one-time use passwords, it seems like there should be a pretty heavy cost to really secure the operating system in this sense. Did you evaluate the overhead for with the encryption enabled?
Yeah, we do not secure the operating system, so we just completely do not trust the operating system.
I'm sorry, I meant the TEE here.
Oh, yes.
I meant, so I guess I'm sort of asking a very simple question, which is, how thoroughly did you evaluate the cost of your encryption mechanism? Did you single that out and sort of look at that in isolation?
Yeah. We completely isolated like the trusted computing base in using a real ARM trust zone. And then we actually observed that the overhead is not, it's actually a little bit large if we have like apple to apple comparison. For example, in this case, our GPU acceleration for the SqueezeNet is like 51 milliseconds, but if we actually implement the work using SecDeep, then we actually introduce another, I think 3 times more overhead because of this encryption and decryption.
I see. Thank you.
Yeah, I got a question. Yeah, first, that's a pretty nice talk. Thank you. And I got a question about the threat model. So you're saying that you completely don't trust the operating system. I'm a little bit curious about the motivation for this definition of threat model. So why is there kinds of any real life example that the operating system of the edge device is totally compromised? What could be the real life example for it?
Yeah. So there are some like kernel APIs that are not very secure. I think like recently we have we have like some attacks, like some zero-day attacks that exploit the non-secure APIs to compromise the operating system. Like for example, I think this is work done somewhere in University of Minnesota. I think it's in this year's IEEE Oakland. I think that what they do is that they basically maliciously injected some like code into the kernel through the community, and then their kernel code, especially for their driver code, has some bugs that might be compromised. I think, I think that there are actually lots of like APIs that are not secure. We actually in the operating system community, we actually have like a list of secure like the secure API list, which means that these APIs are more secure than other APIs. But you know, like in our reality, we are not only using those secure operating system APIs due to the performance issues. If we only, let's say, if we're only limited to those kind of secure APIs, then our performance will be suffered if the developer wants to basically optimize the performance of the device. So the quick answer is there are many kernel calls, many like the kernel APIs that are not very secure, and it could be easily exploited. For example, even though you implement a kernel driver, then I guess that is kind of risky to actually compromise your operating system.
Yeah, that's a nice explanation, but I'm a little bit confused that so if the edge device is actually doing the inference or even training on itself, then there's no need for the edge device to be connected to the internet. Then even if the developer take use of some non-safe kernel core, and they are able to reveal certain information from those kernel codes, but because the edge device is not connected to the internet, then what could be how could it be possible that those information are revealed to real attackers?
Okay, so let's say if you want to update your model, you need to connect it to the internet. And if you're using a phone, I think it has to be connected to the internet for other applications.
Okay, I see your point.
Yeah.
So the attackers may be able to. So the attackers in your setup, you assume the attackers may be able to look at your internet communication and get some revealed information which are revealed by those non-safe kernel codes.
I don't know if I understand your question correctly. So the attacker does not need to access the internet, but they could, let's say, store the information somewhere. Whenever the user accesses the internet, the information will be like uploaded to the attacker's site. More likely, this situation is similar to your smartphone, I would say.
So basically, your assumption is like the attacker might have the ability to change to kinds of change the settings or have some adversarial applications running on my cell phone. So when these inference are running, they might be able to get those information, right?
Yeah, okay. It might be if in the like a very extreme case, it might even be the whole operating system is somehow installed by the malicious hacker.
I see.
Or controlled. Yeah, you can change anything.
Thank you.
Thank you.
And there's one question in the chat box from Apan. So Apan, do you mind to explain your questions to the speaker?
Yeah, I can explain. So I was mainly confused by the goals listed on the problem slide, which was about sensor data confidentiality and deep learning inference code integrity. And I wanted to understand how these are different from, say, model confidentiality and data integrity, and why these are not the goals along with the existing goals?
Okay, that's a great question. So for the model confidentiality, our assumption is that the model itself, like the parameters, are not confidential. They are okay to be revealed.
Okay.
Yeah, we just do not. So this confidentiality just makes sure that the data fit into this model is confidential.
Mm-hmm.
And that's why we split the model, or like the code, to actually compute the model into two parts.
Okay.
Yeah.
And could you also elaborate on the data integrity part?
The data integrity, you mean like the code integrity?
No, more like why the intermediate data of the models are not corrupted when the execution is taking place, and how do you ensure that? Or
okay, so the model resides inside the non-confidential computing base. So the model's integrity is actually the same as how we protect the code integrity. We allocated the same piece of, not same, we allocated like the memory regions that host both the models and the code.
okay. Okay, I have some more clarifications, but I can get in touch with you later for those.
All right, thank you.
Sure.
So any other question?
I had one question. So when you say that like you look at the hash of a particular code to infer whether that got changed or an attacker was able to gain control of the OS. Like since the entire OS is actually under the control of the attacker, is that the only possibility with which they'll be able to like gain information? Or like if some of the APIs got if the hash doesn't change, but there could be like other ways of obtaining data or something like that. Do you anticipate some other issues like that?
Oh, so yeah, that's a great question. So basically what we do in this work is basically encrypt the hash information, and this key is shared with TEE only. The OS does not have that key. So if the OS change, let's say change the hash information, then the TEE will not be able to decrypt it. Or sorry, will not be able to verify its signature.
Okay, got it. Okay. Yeah, thank you so much.
Thank you.
Okay, I think we are close to the end of this session. So if you have any questions, you can email the speakers and you can have a discussion after this session. So finally, I want to thank you, Amit and Renjin, for your excellent presentation. And our next session is break and social. And I believe that this session should be the last session in Zoom meeting today. So please enjoy the rest of CPS and IoT week.